Chapter 29, quiz 1. All right, so pretty short problem, but again, I'm going to use this as sort for introductory purposes. Because now we're on the flip side. This is very much the flip side of chapter 28. Chapter 28 was all about figuring out the force acting on a charged particle moving through a magnetic field. So that's chapter 28, and profoundly important because it's the stuff of motors and solenoids and all sorts of devices that do work for us. Why do we like nature? Because we like to tap into nature. From a practical point of view, why do we like nature? Because we can tap into nature to do work for us. And one of the ways we tap into nature is we tap into nature's magnetic field to do work for us. Like again, motors is probably the easy example. In this particular case, though, we're going to now concern ourselves with magnetic fields created by moving currents. So this is sort of the flip side. So just let's look at B. B stands for magnetic fields. Let's look at B fields created by moving charges. So you could have a proton or an electron move, or you could have a whole avalanche of charged particles called current. And if they move, look at magnetic fields created by moving charges. Again, as opposed to chapter 28, which let's look at the force acting on a moving charge as it moves through a magnetic field. And it kind of sounds like I'm saying the exact same thing, but those are profoundly different subtopics. All right, so here's what we have here. Again, per student feedback, spend a moment of time reading through this. Spend a moment, read through this problem yourself. I'm going to just make some preliminary drawings here. You read through it, try to digest it before I start ranting. All right, let me start. And this was, again, covered in the awe-inspiring chapter 28 lecture videos. But just to reinforce some stuff now, you're looking at a current-carrying wire. You're looking at a current-carrying wire, and you're looking at it in 3 dimensions. And these circles, these concentric circles, represent magnetic field lines. So this is actually an outstanding visual simulation because rather than me standing on my head trying to talk about what it looks like in 3D or you trying to draw things in 3D, which there's a time and place for both of those, you're actually seeing it here. So you can see this wire here. There's a little wire, a little central wire, looks like a little yellow line, and current is flowing through that wire. And this is the big thing about chapter 29.
I don't think we see the screen you're trying to show us.
Oh, okay, thank you. This is the big thing about chapter 29. Chapter 29 is basically saying, apparently when current moves through a wire, it creates a magnetic field. And again, you're looking at a 3-dimensional representation of the magnetic field. If I want to slice, if I want to do plane slicing, this is what happens if I slice along the X plane or the Y plane. And neither of these are really showing what is really happening in this instance, but this is. So this is a current carrying wire, and those concentric circles represent magnetic field lines. And these magnetic field lines actually have a direction. And if you need to worry about finding the direction of a magnetic field line, which you do, then you use pop can right hand rule. And you've seen this before, you're seeing it again now, where you grab that wire as indicated here with your right hand. Like it's, again, I'm always saying, like, you're holding a cup. Here's a cup of water. So you're holding a cup of water in your right hand and you freeze this right hand shape, and then you grab a wire. So if this is a wire right here, I'm grabbing a wire. My thumb points in the direction of the charge flow. In this case, it's current, and your fingers are indicating the circle. So what you see here, this is a 3-dimensional depiction. Well, actually, this is a 2-dimensional plane showing what's happening with the magnetic field lines, both in terms of their shape and direction. Whereas if I went back to this visual here, this is showing that same 2-dimensional plane. What if I, instead of displaying field lines, I display field vectors? That's what this looks like. And maybe if I make things a little denser, okay, maybe if I crank, well, that's good. So, but that's one dimension. That's a one-dimensional or two-dimensional projection. This is what it looks like in 3 dimensions, like that. So I don't know how easy this is to see on my screen to your screen, but again, the chapter 29 video covers this a lot. And again, now you're seeing the directionality of this field. All right, so back to our first quiz. We have 2 wires, 2 very long straight wires in cross section. So we're seeing a top wire and a bottom wire, and they each are carrying a current. And they're each carrying a current out of the page. So that's why we're seeing a dot. So you see a dot right here, and you see a dot right here. Okay. And just a little note, when a dot means it's coming out of the screen towards your eyeball. So whenever you see a dot, it means and it could be current, or it could be a current or an electrical field or magnetic field. It means flowing towards your eyeball, flowing towards your eye. So kind of like this is your eyeball. That's your eyeball, and then flowing towards your eye looks like that. So the dot represents flowing towards your eye, and the thinking is, again, when you see a dot, it's the tip of the arrow. It's a little red dot. Okay. When you see an X means flowing away from your eye. So flowing away from your eye, flowing away from your eye. So here's your eye. Once again, here's your eyeball. And you see it flowing away from your eye. So the thinking there is it's an arrow, and here are the tail feathers of an arrow, just like there's tail feathers to this arrow. But if you see an X, it's because you're looking at the tail feathers flow away from you. So that's represented as an X. So in this case, we have dots because this problem is saying currents flowing directly out of the page. And we know all of the geometry. So the geometry is not a mystery. We're given all of the geometry in terms of the dimensions. The question is, what's the magnitude of the electric field at point P? So you once again hire Probert. You hire Probert to stand right here at point P. And remember what Probert can do. Probert can report on all kinds of measurements, electric field strength, electric force, voltage, and now magnetic field strength and magnetic force. So Probert is, again, just being hired to say, hey, here's the magnetic field I am experiencing at that point, P. Okay, so let me clear this away. Remember this picture. Remember this visual right here, that a current carrying wire is surrounded by concentric, outwardly radiating concentric circles of magnetic field. This is showing the field. It's not showing the direction. You would use your right-hand rule to show the direction. Or in this view, if I wanted to worry about the direction, I would display field vectors, and then there's the direction, and that is pretty intense to look at. So there. This is what it looks like in 3D. There's my direction. There's my concentric circles. So in this particular instance, I actually have to draw a concentric circle. So I might spend a whole bunch of time drawing a whole bunch of concentric circles. I'm just going to focus on the top wire. So what's the magnetic field doing with the top wire? Well, here's a concentric circle. There's another concentric circle. Here's another concentric circle. I don't care about any of those concentric circles. They exist. They exist at all points in space with respect to the wire itself, and they exist all along the length of the wire. But I don't care about any of those concentric circles. I only care about the one and only concentric circle that happens to be encountering Probert, the one concentric circle that is encompassing Probert. So let me just reposition a little bit here. This is the one concentric circle I'm interested in, right? That's pretty good. This is the one concentric circle that I'm going to analyze. The other ones exist. I'm not drawing them because Probert's not encountering them. Let me just do a little adjust. Okay. So that's the concentric circle, but then you have to worry about, well, what's the direction? Right-hand rule says if this wire is coming out of the screen towards your eyeball, do what I'm doing. Maybe here's my wire. I grab hold of this wire. It's the current's flowing out towards my eyeball. So I grab hold using my right hand configuration. My thumb goes in the direction of the current, and my fingers show the direction of the magnetic field at any point. So, for example, and you're going to have to make a lot of these drawings, beyond just today. At this point, the magnetic field is flowing that way, and I'm just drawing the direction of the magnetic field at various points along this circle, which is representing the magnetic field as it exists at point P, which is where Probert is standing. So that's what's going on due to the top wire. Here's what's going on due to the bottom wire. The exact same thing up to a point. Well, let me go back and just give my pitch again. I could spend a lot of time drawing concentric circles around this wire, but I don't care about any of them. I care only about the one concentric circle that is encountering Probert. So that would be this one. Good enough. And then again, you have to worry about direction. So if I'm going to do my right-hand rule, I'm going to do my right-hand rule says at any point, the magnetic field lines are flowing as indicated. So make sure you're clear. This is a common tripping point. I mean, if you can be comfortable with all of this right-hand rule and figuring out directions like this, that simplifies your task enormously. I mean, if you're dealing with equations and math and physics and yet you're not quite solid with the right-hand rules, that really does aggravate things. All right, that's good, I suppose. So now, what's going on at Probert? Here's the magnetic field vector right at Probert's location, right here. Right, it's tangent. Okay, so if I want to know what I know what the magnetic field is at point P. Now I'm drawing the magnetic field vector. So this is magnetic field vector B. And you know what? I better start worrying about top versus bottom. I'm going to call this the magnetic field from wire 1. Okay, and I'll label this wire 1. I was going to say top and bottom, but this is wire 1. I'll just call this number 1, and then this is wire number 2. Wire number 1, wire number 2. This orange vector is the magnetic field that exists at point P due to the current carrying wire number 1. So that's saying a mouthful. If using the same thought process, here's what's going on at point P due to the magnetic field created by current carrying wire 2, which again, I'm drawing a tangent. I'm being really, really cognizant of the fact that the magnetic field vector at any point is tangent to the magnetic field line at that point. So then I will label this B subscript 2. And these are vectors. All right, so that's good. And that's it. So the rest is kind of downhill. The setup was, I think, enormously important. Again, if you're not really comfortable with the right-hand rule and the directions of all this stuff and dots versus X's, make sure you get comfortable. Make sure you ask for assistance if you need it. All right, so then, okay, number one. Okay, I see that B1 and B2 are mirror images of each other. So there's some symmetry. So things are going to get easier. Always look for symmetry. And here we do see some symmetry. I see that B1 and B2 are mirrored across the y-axis, are mirror images of each other, which probably means I should have done this before anything, but I'll do it now. This is, let's decompose B1. Here's the x component for B1. Fine. Here's the y component for B1. Here's the x component for B2. Here's the y component for B2. And you can see there's some destructive interference and some constructive interference. And I'll make note of that right now. This would be B2x. B2x is going to the left. B1x is going to the right. B1y is going straight up. B2y is going straight up. And that's why I'm going to say here in step number 2 that x components cancel and y components reinforce. So B sub x's cancel and BY's reinforce. BX's cancel, refer to drawing. Okay, so number 3. So let's just find B1y and double it. Let's find B1y and multiply by 2. Okay. And we've done this thing. We've done this sort of thing before. Apply this. Let's apply this. B equals mu naught I all over 2 pi A. Again, this is very much central. This is like, this is very central to the chapter 29. Now, so let me just call out a few. Let me give it a quick introduction. This is the current in wire. This A is distance from wire to probert, from wire to probert. And probert's is standing at some point in space, reporting on all sorts of things. This is the permeability of free space. Permeability of free space. You might remember, well, we've had this before, I think. Permeability of free space. It's a magnetic field friendliness factor. Magnetic fields like to travel through some materials much more than others. For example, a transformer. You see a lot of soft steel or even soft iron in transformers because iron is very friendly to magnetic fields. So it's a friendliness factor. And for a vacuum, it has a value of 4 pi E minus 7. And then as long as I'm here, just because I can't remember, and I just want to do this anyway. Let's see. Let's just do what must the units be of mu naught? Well, mu naught apparently equals B times 2 pi A over I. So from a dimensional point of view, one way to represent mu naught is Tesla meters over amperes. So that is a way. And then you can probably decompose that into other equivalents. But this is it. This is a key building block for chapter 29. This is the magnetic field that exists at a given point, a distance A away from the current carrying, from the source, from the source. It could be a current carrying wire or just a charge moving through space. Okay, so that's a big deal. And all we're going to do is apply that. All right, so let's just do, now we're into the operational phase. So that really is the big physics. So the major physics underpinnings and conceptual subtopics and right-hand rules and dots and X's, that's all behind us. Now we're just going to do operational stuff. B1y, once I get B1y, I'm going to double it, equals B1, and then I guess I'm looking for an angle here. So what would be a good angle to deal with? Maybe this angle here. Probably doesn't matter. I'm just kind of pulling something there. So I'm going to call this theta, I suppose. So here's my right angle triangle, because I know the x component and y components are perpendicular. This again, this is B2 vector. Maybe get rid of this over here. Sorry, get rid of this. So I'm just drawing B2. I'm making it clear that B2 is the hypotenuse of that rectangle. And there's B2y. So I'm going to get B1y equals B1. Oh, except I'm saying B2. Yeah, so here. B2y, which I will double, equals B2 sine theta. Okay, so then number 6, B2y, get that number, double it, equals B2. Well, here's B2, mu naught I, and just so we're airtight, I need a subscript there. B2 is the magnetic field created by the current flowing through wire 2. So I'm going to give that a subscript number 2, all over 2 pi times the distance between probert and wire 2. So let me make that super clear. This is the distance I'm talking about from probert to wire 2. There's wire 2. Apparently I'm calling this letter A. This is letter A. All right, so A is the distance between probert and the current carrying wire. Here's probert, here's the current carrying wire. So there, I guess I'll just write that as A. And then again, sine theta. So let's just talk about what A is. A is Pythagorean theorem. You can just say A. Pythagorean theorem is going to get you A. So according to my geometry here, and again, I'm using Pythagorean theorem because I have a very simple right angle triangle. There's my right angle triangle. So Pythagorean theorem says to take d1 over 2. So it's d1 over 2 squared plus d2 squared. And you know both of those numbers. Both of those numbers are provided to you. Again, I think we have all of the dimensions we need. So there's A. So we now have A in this number 6. I2 is given 4.31. And now let's talk about theta. And then it's off to the calculator. Let's see, number 8. Theta's right here. So maybe I'll do this. That's 90 degrees. This, maybe I'll call this alpha. All right, can I figure out alpha? Yeah, I can figure out alpha. This alpha here is going to equal arctan of D1 over 2, side opposite over side adjacent, D1 over 2. So side opposite is D1 over 2, side adjacent is D2. So I don't know what theta is, but I do know what alpha is. So I'll leave the rest to you because let's see, here's my alpha. And I know that this is a right angle right here. So I think I'm going to be good to go. That's 90 degrees. All right, so you're going to be in good shape. So then, once again, solve number 6 and double. And double, and you'll be done. Okay, let's all do that. Let me write down mu naught. Again, mu naught. There.
Professor?
Yep. Yes.
Could you explain how to find theta again?
I'm leaving that up to you. Trig. I'm saying here and you don't have to use this as the theta. You just need to do whatever you want to do to find that component, that y component. So I'm saying, well, I know that this is a 90-degree angle. And I know that so that's 90 degrees. I know I can find theta. So if you know that that's 90 degrees and that's theta, give yourself a chance. Give yourself a chance and try to figure out the trig that's needed to get theta, or take an equivalent approach, and different but equivalent. I can do this too, since I'm talking about if that's alpha, then this is also alpha. So just not to hopefully spill too much, but you can see that I guess you could say, and it's kind of getting hard to look at here, but 90 minus alpha, well, you can see here that if I take this alpha right here, this alpha plus this theta, I mean, kind of hard to look at, but this alpha that I'm highlighting plus this theta that I'm highlighting equals 90. So in equation form, alpha plus theta equals 90 is one way to do it.
Or would it be alpha plus theta equals 90? Because you have to include that entire angle, right?
Well, that's where my drawing might not be incredible. Let me make my drawing maybe a little bit easier. Okay, so that's hopefully. So all I'm saying right here is this alpha that I'm drawing in purple plus this theta that I'm now drawing in purple, those two add together to equal 90. Which is what I have here. Okay, let me see how things are going. Chapter 29. Okay, maybe some more time. Yeah, I mean, it's a calculator workout. I mean, the calculator part's pretty heavy and there's geometry and trig, but the physics is what I needed to stress. You're going to get the operational stuff. Might take a minute, but we'll, you guys keep working on this. And for those of you who are done, let me unleash the next quiz.
Professor?
Yep.
Could you quickly explain again how you got the direction of the magnetic field? Like
yeah, for sure. That's an essential question to ask. So, all right. So Serena and everyone, do you agree? Should I talk about why the direction of this top magnetic field, this top magnetic field is created by wire number 1, which is the top wire. So the magnetic field surrounding a straight current carrying wire is going to appear as concentric circles radiating outward from the wire as you go from close to the wire to further away from the wire, and then all along the wire, from the start of the wire to the end of the wire. And it's right-hand rule. It's the Popcan right-hand rule. It is this right-hand rule that you apply. One second. It is this right-hand rule. Right here. Okay. It is this right-hand rule that you're applying. So if you apply this right-hand rule to our given situation, thumb goes in the direction of current, fingers indicate the direction of the magnetic field. You know they're concentric circles. So really all you're using this right-hand rule for is to get the direction. But if all that's making sense, hopefully the direction of the magnetic field created by the top wire is making sense. And then I'm saying, well, again, just focusing on the top wire at point P, which is right here, at this point right here, point P. Well, I know what's going on with magnetic field line from the top wire. If I want to know what's going on with the magnetic field vector, so again, it's the difference between a field line versus a field vector. A field vector is perpendicular. I'm sorry. So a field vector is tangent to a field line at any given point. So at this point that I'm circling here, tangent means this arrow, this vector here that I'm highlighting in green. That's why the magnetic field that exists at point P due to that top wire is pointing in the direction indicated. And then you have the exact same conversation for the magnetic field created by the bottom wire. And it's hopefully you're seeing again, right-hand rule says that, well, if my thumb points in the direction of the current, which is coming out of the page, my fingers are wrapping in the direction of the magnetic field. And at point P, which is where probert is, now I actually have this tangent. This is the tangent to the magnetic field line at point P. And that's why I drew vector B2 the way I did on the screen. So is that it? Did I cover it, or is there more? Is there anything that's less than clear?
That was good. That's all I needed. Thank you.
Yeah, that's to me, that's the heavy lifting. I mean, yeah, there's trigonometry and calculator stuff and Pythagorean theorem, but let's see how people are doing. Well, here, our next problem. Chapter 29, quiz 2. Give me a moment. Chapter 29, quiz 2. It's now 1:50. Okay, so open up chapter 29, quiz 2, and do the thoughtful read through. Yeah. Similar. Similar, but different enough to be useful. All right, I'll start reading through this. But again, make sure you give it a read through. Maybe I'll take another moment. We need to find out what the magnetic field is in the center of this 4-wire configuration. What is the magnitude of the net magnetic field at the square's center? So I'll just draw some guidelines here. Where's the center of the square? The center of the square is at this intersection. So you've hired Probert, and Probert is going to stand right here. Probert's standing at the middle of that square, and Probert's going to report on the magnetic field strength at that point. And I have 4 wires, so this is not 2 wires; it's 4 wires. So this might go quite a bit faster since a lot of the basics, but this will be good reinforcement. All right, so it says wire number. The currents are out of the page in wires 1 and 4, so those get a dot. Wire 1, the wire 1 current gets a dot because dots are what we use to signify coming out of the page. Wire 1, currents out of the page. Wire 4, currents, except it says, yeah, out of the page. Those get a red dot. And into the page in wires 2 and 3. So wires 2 and 3, those get an X. Except that, why did I draw that? So wires 1 and 4, so error correction. Wires 1 and 4 get a dot. It's the tip of the arrow. Wires 2 and 3 are going into the page, meaning away from your eyeball, meaning tail feathers. There's a tail feather, and there's a tail feather. Okay. All right, so let's just play the game. Interesting. Let's focus on wire number 1. I'm going to draw a whole bunch of magnetic field lines, and let's see. Well, it's a current carrying straight wire, so I don't know everything, but I know I have concentric circles. So if I'm standing at this point, that's a concentric circle at that point. If I'm standing over here, that's a concentric circle that intersects that point. If I'm standing over here, this is a concentric, but I don't care about any of those because I care about Probert. So I'm going to draw the one and only magnetic field that is crossing Probert's position. It will look like this with some trial and error here. So right there, and maybe a little bit smaller. So this is it. You are looking at the one and only magnetic field line that is crossing Probert's position. Perfect enough. Okay. So what about the direction? Again, if you're using this pop can right hand rule right here, your thumb points in the direction of the current flow, which is out of the page, and your fingers are showing the direction of the magnetic field line. So all along this green circle, I'm going to draw arrows that look like this, because that's what my pop can right hand rule indicates. And then right there at point P. So as long as I'm there at point P, I'll finish this just for the sake of completeness. What is my magnetic field vector? All right, so this would be my magnetic field vector at point P due to wire 1. It's tangent. It's tangent to the circle at that point, which also means it's perpendicular to that radii that you can see there, and that's a useful mention, I think. So I'm gonna indicate that, yeah, this is a right angle here. Tangent to that arc means it's perpendicular to that radius at that point. So in all of this field vector needs a name, and this is going to be the magnetic field at point P generated or created by current flowing through wire 1. So that's B1 vector as opposed to B1 field. This is magnetic field. This is B1 field. This is B1 vector. Okay. So if we play this game a bunch more times, which we will, but maybe fast tracking a bit, I can take advantage of symmetry and say, well, here's, I'll play the same game for my bottom wire, and I'll play the same game for, for my wire number 3. And I'll play the same game for my wire number 2. And that's probably a decent enough drawing. Okay. The only thing we have to worry about now is the direction of these field lines. So let's focus on wire 4, since that was the second one I drew. If I'm going to use the right-hand rule the right way, if this current is coming out of the screen, a dot means it's coming out of the screen towards your eye, then my right-hand rule tells me I'm going to have field lines flowing like this. And that means right here at Probert's location, I have a field vector that looks like this. As soon as I move it. Okay. And that would be B4. Yeah, pretty good, I guess, like that. Good enough. This is the magnetic field that exists at point P due to wire 4. So this is B4 vector, whereas this is B4 field. B4 field versus B4 vector. And I need to make sure I'm drawing that tangent I want to draw B4 vector tangent to this point, which means perpendicular again to that radius line, this radius. So that's this perpendicular here as well. All right, so then I'm going to play the same game for 2 and 3. If I play the same game for 2, though, things are a little bit different. Current's going into the page, which means my field lines are flowing like this. So this is kind of seems confusing, but first of all, I need to make sure, am I drawing my field direction correctly? For the magnetic field created by wire 2, the current flowing into the page through wire 2 at point P. Let's see, this is what I'm doing. I think that's right, which means this is my B2. That's my B2 field. So this is my B2 field. What's my B2 vector look like? My B2 vector, I better go to different colors. This will be my B2 vector, like that. Okay, and it looks kind of like it's overlapping B4. And it might be identical to B4 because of symmetry, but I don't think it is identical because they're carrying different current values. But that's B2. So there's my B1 vector, my B1 field, my B4 field, my B4 vector, my B2 field. I have one more to go. And that's wire number 3. So if I use my right-hand rule, it's going into the page, it's flowing this way. It's flowing this way along this field line. And at point P, it's flowing like that. So I have this kind of similar. This is the magnetic field at point P due to the current flowing through wire 3. Okay. So this is B3 vector, which is tangent to B3 field, which is right here. All right, so let me make sure I have everything. Let's see, I'm just going to do an inventory. B1 vector, yes. B1 field. Okay. And does that make sense? B2 vector, okay. B2 field, okay. B3 vector, right here. B3 field, B4 vector here. Okay, a lot going on. You can see this is tricky until you once you digest it, it goes pretty quick. But I guess this is what I'm going to do: superposition, which is basically just a pairing exercise. Number 1, let's see, the magnetic field at point P, where Probert is standing, is just going to equal, is that what they're asking, the net magnetic field? Maybe I won't even, yeah, I'll take it. I shouldn't have used the term superposition. So I'm going to say I'll do this. BP, I can use a lot of symmetry here because each wire is carrying the same current. All right, so I'm going to back off a bit and say, because of symmetry means all B1, B2, B3, B4 X components and Y components are equal in terms of magnitude. R and Y components are equal in magnitude. And again, a nice little wrinkle of this. What if this appeared on exam 4 and we didn't have all of this symmetry and simplification that we're about to go into, are equal in terms of magnitude. So once again, we can see some cancellation. You can see that all of the X components are going to cancel. So all BX components cancel. So that's quite the whittling down of complexity. All BX components cancel. Destructively interfere. All BY components, and I'll use that term because that's a term that does come up. Components. All BY components constructively reinforce, to use a wave dynamics term. Constructively reinforce. So if that's the case, let's just say B1 at point P equals 4 times B3 net. And I'm saying B3 just because it caught my eye. Okay. B3Y. All right, all I'm going to do is I'm going to take vector B3, which took me, a ton of work, a ton of thinking just to get to B3. If it's right, I'm going to take this B3 vector right here and then look at its Y component. And this, I guess this would be the Y component for B3. Looking like this. This would be B3, the X component. And this would be B3, the Y component. So this is B3Y, and this is B3X. All of those X components all collectively cancel. All of the Y components reinforce. So that's why number 3 looks good to me. Unless you guys see a mistake, and please don't delay in shouting out my mistake. So at point P, I'm going to take 4 times B3 times sine theta. Well, here's theta. Things are getting messy, but if this is theta, that's theta. So B3 sine theta will get me the Y component, B3 sine theta. All right, so let's just run with that. What is 4 times B3? Well, B3, again, remember, this is sort of a cornerstone relationship. The magnetic field due to current carrying straight wire is mu naught, the permeability of free space, times the current flowing through that wire over 2 pi A, where A is the distance from probert to the source wire. So just plugging that in here, I have mu naught, subscripts are critical, the current going through wire 3, so that's why that's a subscript 3, because it's the current going through wire 3 that creates the magnetic field B3, all over 2 pi A. What is A? A, it's kind of an unfortunate choice, but maybe, you know what I'm going to do? I'm going to change this from A, because A is already used, R. So just to avoid confusion, 2 pi R. And then what's the distance between probert and wire 3? So let me erase some stuff here. Here's probert right here. I'm going to erase all of this actually, since I've already I think got what I need out of the stuff I'm erasing. Probert is sitting right here. Probert's sitting at the dead center of that bounded square. This is the distance from probert to point P right here. There's probert, there's the wire 3. And I guess if I'm looking at trig here, let's see, this would be A over 2. This would be A over 2. So this would be A over 2 root 2. Okay, so that's it. So the distance between probert and the current carrying straight wire, I keep saying straight purposefully, We'll get into arcs and solenoids soon. But this is a 2 pi a would be, the distance would be a root 2 all over 2 times sine of theta. And let's see, well, you can see if this is B3 right here, if this is B3, and I call this theta, if I remember correctly, you can see theta equals 45 degrees. Theta equals 45 degrees because we're just dealing with a square. This is 45 degrees. Okay, sine of 45 degrees. Let me know if you see any mistakes or have any questions, especially the great thing about this problem, look at all the field vectors and field lines you drew and look at all the right-hand rules and X's and dots. So hopefully this reinforces a lot. So work on that while I go forward with quiz 3. So in the figure below, 5 long parallel wires. So these wires are long, but they're perpendicular to the screen. So they're coming out of the screen and going into the screen. We know their separation distance. And then we have some currents going into the page. So some currents, so I need some X's. Here are the currents going into the page. I1 is going into the page, so that gets an X. Into the page means X for I1. I3 is also going into the page, so that gets an X. I4 is going into the page, so that gets an X. I5 is going into the page, so that gets, all of these are X's except for current 2. Current 2 is out of the page, and all of these currents are different. So there might be some simplifications we can do, but not as much as last time because these are all different current values. So current coming out of the page means a dot for wire 2. Okay, so that's how you do the dots and X's as far as the current. Because remember, you use dots and X's for current direction. You use dots and X's for magnetic field direction, electric field direction, any vector. Any vector could be signified with a dot or an X. All right, so having said that, you need to figure out what the force per unit length is for wire 3. So that means this. Here's the dollar sign. The force, the magnetic force acting on wire 3, and I'll call it net. The net force acting on wire 3 per length. So it's not F you're after, it's force per length because that's what the question says. What is the magnitude of the net force per length? So that's why I'm saying this is the dollar sign. That is force per length. Okay, so there's quite a bit of new stuff here. Here goes. You remember this from chapter 28. The magnetic force acting on a charge is Q V cross B in terms of cross product notation equals QVB sine theta in terms of magnitude angle. And then what I did in the previous conversation in your green sheets, I said, I'm just going to multiply by seconds over seconds. And when I multiply by seconds over seconds, I can't help but notice that Q per second is current. So this is how I get I, because Q over charge per second is current. And then if I look at velocity times time is distance, because I remember the basic definition of velocity is distance over time. So distance equals velocity times time. So it's I times L times B sine theta. IL B sine theta. This is basically for a charge for a charge. That's the force acting on a charge as it moves through a magnetic field. This is the force acting on a bunch of charges or current. The force acting on a current moving through a magnetic field. Okay, so we've seen this before. And again, this is a chapter 28 feature. The magnetic force acting on a wire exposed to a magnetic field is IL cross B or ILB sine theta, just to repeat that. But then the question is, we can say something about B. This B in this expression, B comes from B comes from current flowing through another wire. B comes from current flowing through another wire. That's all I need to say. So that's it. So now we can use superposition. Maybe I was thinking of this problem when I thought of that term superposition. But before we do, you need to figure out the force per unit length for wire 3. So this is our primary focus. We're focusing on wire 3. So let's just go ahead and set up the superposition. The net. Well, I'll do this. The net magnetic field. The net magnetic field at wire 3, which I can just indicate as B3 net, is just going to equal the magnetic field due to wire 1 plus the magnetic field due to wire 2 plus the magnetic field due to wire 4 plus the magnetic field due to wire 5. So I didn't forget 3, but 3 is the current carrying wire. Okay. So that's what I have to do to find my net magnetic field. So let's do this. Let's just do B1. B1 equals, again, mu naught I, have to use subscript 1, over the distance between 1 and 3, which is 2D. Okay, and let's focus on this. And then we have to worry about direction. So I'm going to do this one more time. It's going to get irritating. Maybe it is already, but what's the magnetic field vector at wire 3 due to wire 1? This is a job for a whole bunch of concentric circles, but I don't care about any of these concentric circles except for the one concentric circle. And I'll do this maybe one more time because I think you guys are seeing it. And let me know if you're not, but here's the concentric circle centered on wire 1 that encounters wire 3. So centered on wire 1. That's pretty good right there. All right, so I have to worry about direction. So the direction arrows for this purple circle, which is the B1, this is my B1 field. This is my magnetic field from wire 1, and it has a direction going clockwise. So if it's a clockwise magnetic field at wire 3, which is, I guess you could say where Probert is standing, this is the magnetic field vector at wire 3. It's going straight down like that. Okay, and I will label this B1 vector. That is the magnetic field that's encountering wire 3 due to the current flowing through wire 1. Okay, so now if we play the same game, for wire 2, I'm going to play the same game for wire 2, and I can see that I'm going to have, I guess I'm going to use a whole bunch of different colors to keep things straight. Here's the magnetic field at wire 3, and then try to maybe ignore me and just do your own thought process. But this would be the magnetic field at wire 3 due to the magnetic field created by wire 2. So that's B2 vector. I'm not going to draw B2 field. I guess I'm just going to draw B2 vector. And then if I play the same game for wire 4, here's wire 4. And this is hopefully the jumping off point. Hopefully you're okay with me just drawing the results without giving the whole backstory, but it would be great just to ask questions if you're less than clear. So this would be B4. Not sure about the lengths, but I do know it's going straight up. So this is B4 vector. Is it? Yes, it is. That's B4 vector, and I'm not showing B4 field. What about number 5? Same thing, different color and thicker. Okay. Right. Okay. So this is B5 vector. This is the magnetic field created by current flowing through wire 5 as it exists at point P, which is where wire 3 is. So this is B5 vector. Okay, that's it. 3 up, 1 down. Okay. All right, so you know what? Here's my step 3, I guess. I'm going to say the net. The net magnetic field, B3 net, as I've already said in line 1, is going to equal B1. All right, so here's B1, mu naught I1 over the distance between wire 1 and wire 3, which is 2D. So I just repeat. But you know what? I'm going to do a negative because that's going in the negative Y direction. Plus, here's the contribution from wire 2. Mu naught I2. What's the distance? What's the distance between wire 2 and wire 3? It's 2D. I'm sorry, it's 1D. Okay, done with B2. Here's B3. I should say B4. B4 is mu naught times the current flowing through wire 4 all over, and I forgot my 2 pi's. So this should be 2 pi. This should be 2 pi. This should be 2 pi. The distance between 3 and 4 is D, and that's also a plus. And last but not least, here's the magnetic field, mu naught I5, created by current 5, 2 pi. What's the distance between 5 and 3? It's 2D. So I think you're done because you obviously can pull out common factors. So go ahead and pull out a mu naught and a 2 pi. So mu naught over 2 pi is a common, no, mu naught 2 pi D is a common factor. And you're done. Oh, no, you're not done. So because what you're going to do, well, you're done finding the net magnetic field. So great. I know B3 net. But you're not done because now apply the force acting on a current carrying wire. Now you apply F equals ILB sine theta, where once again, theta in this magnitude angle expression refers to the angle between these two neighbors. What's the distance between vector L and vector B? Well, vector L, little sidebar, vector L is perpendicular to the page. So L vector is perpendicular to page. B vector is in the plus or minus Y direction. B vector is plus or minus J hat. So theta equals 90. Okay. So you know what theta is. Now we just have to worry about subscripts. So I'm going to do one more rewrite, number 6. The magnetic force acting on wire 3 because of those nearby wires is number 6. F3 net equals, once again, the current going through wire 3, IL, the length of wire 3 times B3 net, times sine of 90 degrees. But I'm just note to self, we're not after F3 net. We're after force per length. So we're after force per length. So then it's I, which is the current going through. So you got to keep, it's murder trying to keep track of all these subscripts, but if you're meticulous, you'll be okay. I3 times B3 net sine of 90 equals 1, and you're done. Where again, this net magnetic field, got produced or got calculated from step number 3. And I3 is given. Chapter 29, quiz 4. Here's the lecture notes. So in the chapter 29 lecture notes and lecture video, there's a whole section dedicated to Ampere's law. This is in many ways the magnetic equivalent to Gauss's law. So if you remember chapter 23, Gauss's law, that pertained to Gaussian surfaces and the amount of charge enclosed by a Gaussian surface. So if you go through, and again, I keep recommending that you do more than just fast forward to the final result. You actually live through the derivation and ask follow-up questions about the derivation. Why? Because it makes you a better problem solver. It makes you smarter if you know the derivation, if you learn from the derivation. But that all happens, hopefully. Hopefully you will learn and get smarter from boxes 1 through 14. But the final result is box 14, which is Ampere's law. And that's what this problem is all about. So I copy and pasted Ampere's law in my notebook right here. This is very similar to Gauss's law. This, let me just dissect this a little bit. This is the current enclosed by an Amperian loop. Amperian. So you remember the term Gaussian surface. Now we use the term Amperian loop. So again, this is sort of the magnetic field equivalent to Gauss's law, which pertained to electric field. So there is something called the Amperian loop, and an Amperian loop encloses an amount of current, and this is the expression for this is closed loop integral. This is closed loop integral. So a closed loop integral means you do not specify an initial or final position. You do not specify a boundary condition because you just integrate along the whole loop. So for example, if you had a circle and I wanted to integrate, and I had and this is ds, the closed loop integral of ds would just be s, which equals 2 pi r. So if you notice what you don't see in a closed loop integral indicators, you don't see anything mentioning boundary conditions. You don't see that specification. It's not an indefinite integral. It's definitely a definite integral, but again, you're just starting and ending at the same point, which is in a closed loop is the entire loop. This is the magnetic field. So this is the magnetic field. This is the magnetic field created by I enclosed. And this is the path length of the Amperian loop. So that is the dissection of Ampere's law. So this problem is kind of like, it's I don't want to say gimmick, but it's a little bit gimmicky. I mean, it's legitimate. But here's what you got to do. The question is, you need to find this expression. So you don't need to find the magnetic field or the path length of an Amperian surface. You need to find out the result of this entire term. What is this result? So this result, the closed loop integral of B dot ds. Now, one thing, again, and this goes into the deep dive from the lecture video, the chapter 29 lecture video in green sheets, is this is a dot product. So for some reason, we apparently are caring about product of parallels, and you should know why. And the why is right here on your screen because of how we're setting things up. Really, the why is spelled out in box 6. But if, I mean, it's one thing just to apply this result, but it's another thing to know why you're taking the dot product. And this is why we're taking the dot product. I don't want to read through all 14 boxes because that's in the lecture video. But anyway, just giving a little sidebar advertisement for the lecture video. I don't know how to do the, I don't have, this is not solvable. This is not solvable based on information I have at hand. But you know what is solvable? This is solvable. This is solvable. So this is solvable because you know the result for mu naught, which is permeability of free space. So this is solvable once you figure out what the enclosed loops are, or what the enclosed current is. So it says 8 wires are once again perpendicular to the page, meaning coming out of the page towards you and coming out of the screen towards you and going into the screen away from you. And let me erase some stuff here. And it says there's a labeling scheme. So we have an index K equals 1, 2 through 8, where the wires with the odd K numbers are the currents coming out of the page. So let me do that. So odd K means out. So odd K means red dots. I'm just reading the problem. For those wires with odd K, the current is out of the page. So this is out. 1, 3, 5, 7. Is that it? I guess so. 1, 3, 5, 7 are odd. So the current's coming out of the page. So those get dots. Going into the page are the evens. For those with the even K, it's into the page. So 2 gets an X. 4 gets an X. 2, 4, 6, 8. Okay. So those are our current directions. So number 1. Find or identify the closed. It's good to write closed because all Amperian loops are closed. Identify the closed Amperian loop, which it's given to you. Although you do have to kind of still think on it a little bit. Identify the closed Amperian loop. Step number 2, find the net. Find I enclosed. Find the enclosed current. Because once you find the enclosed current, then again, you're just going to multiply by the permeability of free space. So find the enclosed current. So now you just have to be, well, before I leave you to thinking on this, just to get you kickstarted a little bit, I1 equals Ki odd K1. So equals 1 times I 1 times I, or my number is 4.64 milliamps, which is equal to 0.00464 amperes. So don't forget about that conversion. So I2, it's the same thing. It's 2 times I. So it's just going to be, I'll just equals 2 times I, and then so on and so forth. So I8 equals 8 times I. So I'm just wondering, what else do you need? So this is a big thing. Identify the Amperian loop. So figure out what's in. Find I enclosed by the Amperian loop, by the Amperian loop. And I guess I'll give one hint. I think I'm not sure that all of those currents are inside of that Amperian loop. So find I enclosed by Amperian loop. So I'm not saying, maybe all of those currents are enclosed by the Amperian loop. I wouldn't assume that. I'm thinking maybe some of those currents are inside of the loop. Some of those currents are outside of the loop. So you have to do your visualization. And then once you figure out what's in and what's out, you basically sum them up. So I'm going to call any current that has an X. So any current that has an X, I'm just going to consider that negative. We're just dealing with magnitude, so I'm just trying to find the difference. Any current that has an X makes a negative contribution. Any current that is coming out of the page like that is making a positive contribution. All right, so your job is to find out, number one, what are the currents? What's the Amperian loop? And it's given to you. You are given the Amperian loop, so you're done with number one. Number two, what's the net current enclosed by the Amperian loop? Find that magnitude. Remember, X's are negative, dots are positive. And then once you find the net current using this scheme, using this indexing scheme in number 3, then just multiply by mu naught. So this would be number 4. Answer is mu naught times I enclosed. That is our $sign. Okay, so you guys can work on that while I call up quiz 5.
So did we just like assume that the X's were negative and the dots were positive, or is there a reasoning?
No, all I know is that whatever they are, they're offsetting.
So we just know that they're opposite.
What's that?
We just know that they're opposites.
Yeah, right. So it's conventional because we're just dealing with magnitudes. We don't, there's no such thing as a direction when it comes to getting this answer does not come with a direction. So we just need to worry about magnitude. Okay, let's go forth. New territory. Chapter 29, problem 47. This is the chapter 29, quiz 5. This is new. So what I'm drawing here, I kind of did some drawing here in my spare time. You're looking at a long cylindrical wire. So let's just make sure everything gets labeled. This is a long cylindrical wire. So it looks like a cylinder, long cylindrical wire. That's what we are looking at. It says the current density inside of a long solid cylindrical wire. So long solid cylindrical wire has a certain current density. And in chapter 27, and this is going to sound a little bit obscure, but let me go to my chapter 27 green sheets. You have those. Chapter 27. In chapter 27, this actually was introduced. So let me share this. Chapter 27 had right here in box 10, there's something called current density. And it's yet another density. So it's just current per cross-sectional area. So there's a good visual. So you're looking at this, you're looking at a cylindrical wire on the screen. Again, this is a good visual. It mirrors, it depicts exactly what we're looking at. And the current density is basically, you know, the amount of current flowing through an imaginary cross section. So you can see here, there's some angle theta, which means if theta equals 0, that's going to give me the maximum density. Because if theta does not equal 0, I'm having some amount of that current that is not passing through that cross-sectional area. It's actually going within the plane. It's not entering or leaving that cross-sectional area. So with that in mind, let's jump into this problem. We know the current density. So number one, I'm going to start there. Well, if we know the current density, and then you tell Probert find the magnitude of the magnetic field at a distance of r equals 0. So I'm gonna do B, and then you can do C. I'll do B. One is done, so we're done. Find the magnitude of the magnetic field at its, so in general, for a long straight wire, for a long current carrying, you do kind of have to say all of this, for a long current carrying straight wire, the following is true. For a long current carrying straight wire, once again, B equals mu naught I over 2 pi A, where A is the distance from Probert to the wire, the current carrying straight wire. So for part A, we're done. So here's the answer to part A. For part A, if R equals 0, then I equals 0. Then I equals 0, which means B equals 0. Okay, so that's done. If there's no enclosed current, if there's no current at R equals 0, there is no current. And I guess you could argue it's undefined because it's sort of implying you have 0 over 0, which is undefined. So, but I look at it more from an Ampere's law point of view. At R equals 0, there's no enclosed current. So I take the Ampere's law way out, which again, Ampere's law says, let's just do a little quick sidebar. The closed loop integral of B dot dA equals mu naught times I enclosed. So according to Ampere's law, I enclosed, let me replace it. Instead of saying I equals 0, I'll say I enclosed equals 0, according to Ampere's law. So if we apply Ampere's law, we're not running into a situation of 0 over 0. All right, so we're done with A. I'll do part B, you do C, but here's part B. Part B, let's do, well, B, what's the magnetic field when Probert is at a distance of R equals 3.5 millimeters? So let's just say Probert, for the sake of conversation, is standing right here. Here's Probert right here. Probert standing, say, right there. Probert standing at some distance, R equals 3.5 millimeters from the longitudinal axis of this cylindrical wire. Okay, so let's go with that. Well, the answer seems to be, this is our first, this is the $ for part B. So then number 5, B equals mu naught I all over 2 pi r. And then I'd say, what's I? Because it was looking plug and play, but it's not what's I. Number 6, well, I know current density. I mean, you guys, we've had linear charge density. We've had linear densities lambda, surface densities sigma, and volumetric densities rho. So this is just another density. A density is just something for something. And in this case, J is the current density, current per cross-sectional area, the current going through that cross-sectional area. And you know what I better do? I better differentialize. I'm going to differentialize this expression because I have a function. I don't have uniform current density as indicated right here. Okay, so this is what I'm keying on. So this is a job for calculus. I have a current density function, which is why I'll take number 6 and I'll just differentialize it. And I'll say, well, if that's true, if J equals current per area, then current equals J dot area. And this is sort of the definitional form. 1 second. But I'm going to have to do it like this. I'm going to differentialize. So differentiate. Okay. So here's the differential form. Ready? I. The current enclosed, this I right here is in fact this I right here. So this is what I'm going after. Okay. So in differential form, it's going to equal the integral of di, which is going to equal the integral of j dot dA. Okay. So the differential form here you could say would be, if I differentiate both sides, di equals j dot dA. Okay. So let's get the total amount of current that's flowing from the point of view of Probert, which is standing at a distance 3.5 millimeters away. So number 9. All right. So the I that's creating the magnetic field at Probert's position is the integral of J, and J is some constant. J naught, I'm just looking at the problem statement, J naught R over A. So this is J naught times dA. So I'll go to magnitude angle, cosine theta. So this is magnitude angle, the magnitude angle version of dot product. Number 10. Theta is, as always, the distance between these two neighbors. What's the distance between the surface normal and the current direction? Okay, so theta equal 0 degrees. And a word about that, just not to sweep it under the rug. Here's the surface normal. The surface normal looks like this. I'll draw, well, first I'm going to identify my surface. Here's the surface that I'm going to have to deal with right here, because Probert is defining the surface that I have to deal with. So if Probert is standing where I indicated at some distance away from the center or from the longitudinal axis of this cylinder, this is dA. This is the differential area through which the current is flowing. Again, think current density is current flowing through an imaginary area, an imaginary cross-sectional area, and that's what I'm drawing right now. So this right here, this is dA. And my dA vector, that's my area, but my surface normal, that's my surface normal vector is perpendicular. So I'll draw it like this, I guess. Here's There's my surface. Here's my surface normal vector, like that. Let me try that one more time. Okay. So let me just keep repeating that. I've indicated my differential area. This is my differential area surface normal. So there's the dA, which is this right here. This whole thing, J, this whole thing that I'm highlighting, this is known as my current density vector. And that sounds weird. You're thinking, wait a minute, how can density have a direction? And it does by convention. This is my current density vector, J vector. And that's what this is. This is showing the magnitude. So current density is a vector, which means it has a magnitude and direction. The magnitude is given right here. So this is showing the magnitude. This is the magnitude. What's the direction? The direction is in the same direction as the current flow. The current density inside a long solid cylindrical wire is in the direction of the central axis. So that's my surface normal vector. This is my current direction, my J hat direction. So let me just draw that and then I'll talk through it again. Ready, set, go. Okay. So this is two things. This is my current. It said the current's flowing in that same direction. It's in the direction of the central axis. And so I'm going to use that as my current direction and the direction for my current density, because that's just the convention. The direction of current density is the same as the current direction. So anyway, that's 8 minutes dedicated to explaining why theta equals 0. But details matter. This is definitely the deep dive. All right, so, but now we're done with the physics, I think. We're done with the physics because we're saying if Probert is standing right here, this is Probert's location, all you need to do is figure out what is the distance from the wire and what is the total amount of current flowing through that wire. So what we're doing, I should maybe add this for step 11. Number 11, I guess we're saying because of symmetry, by symmetry, enclosed current is represented as a line, coincident with axis. Because it's a solid cylindrical wire, but due to symmetry, it actually is represented as just a single line, like a regular one-dimensional wire. And this right here, this is the longitudinal axis. So there's a lot going on here. That's the longitudinal axis. I just got to figure out what that I value is. And I know the distance. So number 9, look at the integral in number 9. So here, I'll say theta equals 0 degrees, just to not forget that. Number 11 is good. Number 12, what's dA? So here, once again, is a quick recap on how to find differential area. So your job is to find differential area. So here's, if I call this dA, whatever that is, this is dA. That's a differential area. This is my cross-sectional area. So this green cross-hatched surface is the same as this green cross-hatched surface. So that surface and this surface is the same. So if I just want, I need an expression for dA. So that's what I'm doing. That's why I'm doing what I'm doing. What can I replace dA with in this? And I'll just say, well, okay, I'll kind of fast track this because I've done this before multiple times. Well, here's an arc length. So all I have to do is to take that arc length and multiply it by, I have to add up all of these arc lengths. And if I stack up all of these arc lengths, I'm going to get that surface area. So I could just say, dA equals one arc length, which is r d theta, times dr of them. R, dr, yeah. So that's good. So this is dr, and this is theta. Okay, so let's put all of that in an integral, and I think we're almost done. Number 12. The enclosed current equals, pull out, I'm looking at number 9, pull out the constants. J naught is a constant, little a is a constant, cosine of 0 is 1, so we're done with that. Integral, and then we have to worry about our boundary conditions. I need to go from 0, which is right here. 0 starts at the center of the circle, which is right here. Here's 0. And then I need to go all the way out to r. So from 0 to r, I guess, I'll just leave it as, for part B, it's 3.5 millimeters, 0.0035 meters, times r, try that one more time. J naught times r over a. So I got J naught over a taken care of. J naught times r over little a times dA. And here's dA. A would be 2 pi r dr, because here, I guess I should finish up this sidebar here. So dA equals, I could say r dr integral of d theta from 0 to 2 pi equals 2 pi r dr. So this is the courageous way to cough up a dA, variable of integration. Here's the low-hanging fruit approach. You know the area of a circle. The area of a circle is pi r squared. So if I differentiate the left and the right side, what's the differential? What's the differential of a? dA. What's the differential of pi r squared? It's 2 pi r dr. So this is, again, the low-hanging fruit to get an expression for dA. This was the more long-winded approach. It's good to maybe see both. But I guess we're done. We're done because number 13. So find I. So find I, and you know all of this. You know J naught. You know how to integrate. You know how to do everything in number 12. I'm going to call this I enclosed just to be a little more airtight. This is the enclosed current. And then once you find the enclosed current from step number 12, go back to number 5. Go back to number 5. And find B. And then the last thing before I fade away for a while is repeat for part C. All right, so I'll leave you to it. You guys finish all of this. I'll hang out, get other stuff ready, look for questions or corrections to a mistake that maybe I made. But go ahead and answer A, B, and C, although the answer to A is done. Chapter 29, quiz 6, which is talking about a solenoid. And again, for those of you who enjoyed the chapter 29 lecture video, I was definitely standing on my head and trying to do anything and everything to underscore the importance of solenoids, just because they are, for good reasons. One of the reasons why solenoids are really important, because solenoids do this. Solenoids store magnetic potential energy, just like capacitors. We like capacitors because capacitors stored electrostatic potential energy. So you always hear a lot of discussion about capacitors being used for like alternative energy or sustainable energy. You have these gigantic windmills that generate electricity, but how do you store that electricity? If you don't use the electricity right away, what do? You have to store it, and that's a huge challenge. So solenoids store magnetic energy. Capacitors store electrostatic potential energy. So they're very much analogs of each other. You remember, here's a capacitor plate. This is the positive side of a capacitor plate, and that's the negative plate. And we like capacitors because they store electric energy. Kevin says his quiz is locked. So you guys, let me know if the quiz is locked. Everyone speak up. Otherwise, because I think Ali, maybe one of the quizzes was locked for you, and Kevin's saying this quiz is locked for him. So let's see. Other than refreshing, Ryan's good with this. So I don't know why that happens. That seems to happen sporadically to some users. Maybe it's just a matter of refreshing. So refresh or log out, log in would be my two things. And something tells me one of those are going to work. So between just refreshing your session or logging all the way out and logging all the way in, that should work. Let me know if it doesn't. You will get taken care of. But again, here's the beauty of capacitors, because look at all of these electric field lines that I'm drawing. And these electric field lines are basically a repository of electrostatic potential energy. So we heart capacitors for that reason. Over here now, I'm drawing a solenoid, and I kind of got this from that simulation app that pays enormous dividends. And let me just go to that one more time. I'm going to go back to this simulation. Falstad. It's a Falstad, so the Falstad is still providing very rich visuals for us. So here's the Falstad simulation. This is the Falstad simulation, and you can see you have a lot of ways to control it, but I want a solenoid. Here's a line. So this is what a current carrying line looks like in terms of, let's just look at the field lines. All right. So yes. So a current carrying straight line is very interesting. What about a current carrying loop? So instead of a line, let's take a wire and make a loop out of it. And that would be called a current loop. There it is. So if you play this right-hand rule game, you would actually be able to exactly come up with this visual right here. Not like that. With this, that's pretty good. So this is what happens when you do that right-hand rule enough times. So if you're patient enough and you're careful enough drawing, I'm kind of fumbling here. Lift up and lift over, and that's probably okay. All right. If you do this right-hand rule business over and over again at every point along that wire, hyperphysics, right-hand rule, because I lost it. Let me go back to my notes. Hyperphysics, right-hand rule, B field. There. Okay, good enough. There it is. All right, so you play this right-hand rule game at every point along that, so current carrying loop. And again, right here, if I click here, bend, so with this in mind, this is a current carrying straight wire. I'm going to click this link right here called bend current into loop. There it is. That's it. So if you play this right-hand rule the right way at enough points, you're going to get this visual right here, which is just what we're seeing right here in Falstad, right here, for a loop, current loop. And we're looking at just electric field lines. All right, so there. And again, this is what happens if I look at it in the X-plane. Perfect. So now we've transitioned from a current carrying straight wire to a loop. What if we have a bunch of loops? So what if I just stack these loops on top of each other? Like there's Probert. So I'm going from current loop to solenoid. There. So this is a current carrying wire, but now it looks like a spring. Or it's helical shaped or spring shaped. It's what you get when you stack a whole bunch of loops one on top of the other. And this is why we like it, because once again, look at the magnetic field inside of this solenoid. I didn't mean to do that, so let me reset. That's interesting. Let me redo that. Okay, so solenoid. It's actually a pretty interesting view. Popcorn or display particles, but we're looking at field lines. And if I just do a slice, I think it was the X slice. Okay, right there. And then maybe if I make this an even longer diameter. So you can see what happens. It looks pretty uniform inside of the solenoid, but I do kind of get edge effects. So if this is a really, that's pretty good too. If this is a really long solenoid, then I do have edge effects, but those edge effects are kind of minimized because most of my magnetic field is well behaved. When I say well behaved, I mean nice and uniform inside of that solenoid, like you can see here. If I have a really short solenoid, then the edge effects kind of dominate. And that's actually a pretty good view right there. So we like solenoids for a ton of reasons. I go much deeper into this in the chapter 29 video, but back to the problem at hand, our last problem of today. Well, let's read through this. You have one of these solenoids, and what I did here is I just copied and pasted a view from that Falstad. Again, remember Falstad circuit? It's the same Falstad, so really, really good stuff. So I just pasted, I took a snip of my solenoid. There it is. And then I kind of redrew it right here. So this would just sort of be a perspective view. I'll label this. This is my perspective view, like whatever that is, 3/4 front perspective view. And this is the same solenoid here, but this is just side view, I'll call it, side view. So it's the same solenoid, just different views. Now what I'm labeling here, you can see it in the animation snip, but I'm drawing these gray field lines, and these are all magnetic field lines. And once again, these magnetic field lines, this is why solenoids are everywhere. You find them in very exotic applications like the Large Hadron Collider, all the way to fuel injectors in your automobile system, all the way to like door locks that are activated by a magnetic key card. So I'm drawing all of the magnetic field lines from the solenoid. So this is the solenoid. This is the solenoid magnetic field lines indicated in gray. And then what I'm doing here, I'm just sort of saying, well, okay, here is the one representative vector. Here's the one vector that represents all of them. So this is the B field vector, and I'm going to do subscript S. So let me just caption that. This is the net magnetic field vector for the solenoid. Okay. So hopefully this is making sense and you're following it and the visuals help. Now what we have here, this green arrow I drew here, this is a current carrying wire. So this green arrow right here is a current. It is a current carrying straight wire. And we've dealt with that before. It's a current carrying straight wire, and this current carrying straight wire creates its own magnetic field. So just for the purposes of reinforcement, if we go back to this simulation and I just say, hey, what does a current carrying straight wire look like again? It looks like this. In 2 dimensions, it creates a magnetic field in an. So if I just say, hey, what's going on in this plane? That's the magnetic field. If I say, hey, what's going on in 3 dimensions? This is what's going on. And you use this right-hand rule to figure out the direction of the magnetic field. We know it's concentric circles, and we use right-hand rule to figure out the direction. So anyway, those are the 2 magnetic fields that I have simultaneously existing in this space. Okay. So it says Probert, if Probert goes to a certain location, I'm kind of drawing that here. So I'm going to just say, it says, where does Probert have to, if I read this, at what radial distance from the axis in centimeters will the direction of the resulting magnetic field be 53.5 degrees with respect to the axial direction? So this is the axial direction right here. This is the axial direction. Okay, so let me just adjust this. I'm just drawing this. I'm just exaggerating the length here because things are getting crowded. All right, so this purple vector, this is the axial direction. So this is our reference, axial direction. This is our reference point. And I have 2 magnetic fields going on at the same time. I have the red magnetic field created by the solenoid. And basically, I'm just drawing one vector, but these vectors exist everywhere inside of the solenoid. So if I wanted to be maybe a little more careful, which I guess I do, I'm just going to draw the magnetic field inside of the solenoid. So I'm just going to adjust this a little bit here. I want to fit this all within the solenoid. That's okay. That's pretty good, I guess. All right. And as mentioned, these red vectors, they exist everywhere. So I have my entire solenoid full of these red magnetic field vectors. So here's another one, and then here's another one. So just like it's this solenoid is completely filled with magnetic field lines and hence completely filled with magnetic field vectors. I'm just drawing a bunch of them. And at the same time, there is the magnetic field created by the wire. So that's where I'm doing a little simplification here because things are getting crazy. I'm just going to do I'm just going to look at a particular loop, right? Like this. So I'm going to take one of those solenoid loops, say maybe just for the sake of conversation, I'm going to take this loop right here and just isolate it just because things are going crazy. So Probert is standing, where does Probert needs to stand? Somewhere here, right here. Probert needs to stand right there. If Probert stands right there, well, I know what the magnetic field is doing from the solenoid. Once again, the magnetic field from the solenoid is just doing this. All right, so the magnetic field vector. So this is the magnetic field vector created by the solenoid. B subscript S stands for solenoid. And then also at this point, there is a magnetic field created by this wire right here. This is my wire. This is the, oh, I already drew that. This is the current carrying straight wire. Current carrying straight wire. So I already labeled that. I already drew that as a thick green vector. And we know that I have concentric circles created. And I'll just sort of arbitrarily say, well, at some arbitrary point, say maybe where Probert is. So Probert is actually standing at some location in space where the magnetic field due to the wire is, I'll just do it like this, is maybe going straight up. It's going around and around in a circle, but I'm snapshotting it at some convenient place. Right. I'm looking for a better pen. Okay, right here. All right, there. All right. So this is the magnetic field, B subscript W for wire, that exists at that green dot, which is where Probert is standing. So again, what I basically did, let me just maybe caption that, is I'm saying, let's just say if I wanted to draw the magnetic field vectors all around that current carrying straight wire, it once again looks like this. So I'm just going to select an easy one. Let's field lines, field vectors, right, like that. And I'm just going to take one that points straight up, just again for the ease of drawing. But you can, hopefully you're kind of seeing the gist of what I'm trying to talk through and draw through. It's kind of hard, but I'm just going to take one of these vectors, maybe this vector right here, and say, well, I'm going to look at that point in space. Look how far I am from that current carrying wire. I'm inside of the solenoid, and that's just going straight up. So that's why I'm drawing things the way I'm drawing them here. And then now we're kind of done. That was the physics, because the question is, what's the radial distance from the axis in centimeters? So if Probert's standing right here, here's my radial, here's my axis, my longitudinal axis, looking like this. Longitudinal, I guess I use purple, so let me just, I'm just going to go from this very busy drawing to maybe this less busy drawing. There's my longitudinal axis. Okay, so then there's my vector diagram. I'll make just a little copy of that. Copy, paste, and there it is. I'll get rid of, move this over. And there's theta right here. This is the magnetic field created by my solenoid. This is the magnetic field created by my wire. And this is theta right here. That's theta. Okay. So, well, let's do this. Step number one. All of this was set up. Step number one, tan theta equals side opposite BW over side adjacent BS. Where's my dollar sign? My dollar sign is little r, I guess. Well, still not seeing my dollar sign, so I'm just going to keep going. The magnetic field created by a wire at some point is mu naught I going through the wire all over 2 pi r. And that's my dollar sign. So there's the appearance of the dollar sign. This whole term right here, this once again is the magnetic field created by my wire at a point. So this is magnetic field created by a wire at a point. That's my numerator. My denominator is the magnetic field created by a solenoid. Using Ampere's law, the chapter 29 lecture video, along with the associated green sheets, derive the expression for the magnetic field existing within a solenoid. It was mu naught N times I of the solenoid. And then I think we're going to be done. This is the dollar sign right here. So let me just, you can see some simplification. Mu naughts cancel. So no need to drag that along anymore. So a couple more pieces of input for me, and then you're on your own. You know the current flowing through the wire. And then you need to divide by 2 pi r. And that r, again, is the dollar sign. And downstairs, little n is the turn density. So little n is the turn density, or number of turns per length, equals turn. So it's basically the spring density, turn density. So it's yet another density. Turn density is number of turns per length. And that's given to us. That's given to us as, for me, it says there are 9.04 turns, and that's not a unit. So it's just 9.04 turns per centimeter. And I'm just going to go straight from centimeter to meter, 0.01 meter. So I'm just going to instinctively go to meters and seconds and newtons and all that stuff. All right, so and then everything else is known. So let me do a sanity check before I exit. Do I know the current going through the wire? Is that given? Yes. The current going through the wire is given. 2 pi is okay. I know the turn density. For me, it's 9.04 divided by 0.01 meters. Is the solenoid current given? Yes, it is. Okay. So then over here, I guess this is just going to be N over L times I. So I'll just leave it like that. You know everything here. And again, this, for me, this is going to equal the tangent of 53.5. 53.5 degrees. And that's the answer to part A. So this is completely done, or this is completely set up for part A. So now you know where Probert needs to be standing. If Probert is standing at this value, whatever this R value is, the magnetic field is going to be making an angle of theta with respect to the central axis. Part B says, what is the magnetic field there? If Probert stands at that location, the angle, the net angle, the magnetic field's, the angle of the net magnetic field is going to make a angle of 53.5 degrees. But what is the value of the magnetic field? So this would be number 2. All of this here, let's see, just use Pythagorean theorems. You can say B net equals Pythagorean theorem. This is a right angle, equals BW squared plus B solenoid squared, and then just take the square root of that, and that's going to give you the answer to part B, where this whole mess right here is, this is BW as indicated. So all of this is BW. Store that in your calculator memory. All of this in the denominator is B solenoid. And then once again, this is BW, B solenoid, and you're done. So that's a lot of talking by me for a new class of problem. By now, hopefully you're sort of seeing a coherent method or a coherent vision emerge in terms of how to do calculus and physics and engineering courses. You deal with a differential element or you deal with an instantaneous change in something and then you differentiate or you integrate. And so this is problem. This is a good problem because it's building block. It's fundamental in the solutions that we're going to use. Now, and I will say, and this is true a lot of times, there's a deep dive on this, but I want to, despite the fact that it's a deep dive, I want to go through this ad nauseum because there's a lot of fundamental points to make, and it's pretty complicated. So let's go. This is do the read through. Read through this problem. I'll be quiet for a few seconds and start drawing some stuff. But read, see what you can gather from your own read through. All right, I'll start. And what I'm doing here, just in the background, I'm using the pop can right hand rule. I'm using the pop can right hand rule to basically tell me what's going on with the magnetic field created by the current going through this wire. So that's what I was doing during my cone of silence. And I need to make sure I'm doing this right. So if this going to, all right, so then we go, the top one would be, so hopefully you're seeing what I'm seeing in terms of what's going on with the magnetic field all along this wire. Okay. All right. And I might have to redo some of those, but here we go. Let's talk about this. Probert, you hire Probert to stand right here at point P, and Probert's job is to tell you what the net magnetic field is at that location. So this is why I said I should have started here yesterday, but it's not a big deal because I'm doing it now. This is the Biot-Savart law. So this was, I think this is where chapter 29 started out. This is a major portion of the chapter 29 lecture video, and it is a major part because of its fundamental nature. So for example, if you looked at your green sheets, this is what I'm talking about. Like this is chapter 29. It starts off with the Biot-Savart law and goes into, actually, there's no derivation here. If you notice, there's no derivation with Biot-Savart law. It's empirical, meaning that Biot-Savart did a whole bunch of experiments and coughed up this expression. So I'm glossing over these boxes because you have access to the lecture video and the lecture notes. However, I'm still going to reinforce some stuff. This is the Biot-Savart law, and it basically does the following. It relates the following. It lets you pull together the correlation between wire length and current going through the wire and the magnetic field and proximity. So it's tying together those four things: magnetic field. How does the magnetic field relate to the current going through a wire? It doesn't have to go through a wire, but we're saying it goes through a wire. How does the magnetic field relate to the current going through a wire and the shape and proximity of that wire with respect to a point? That's all it's saying. This was not a derivation. Basically, you just treat it like a lab and you systematically hold some sets of variables constant and vary others. And when the smoke clears, you get the Biot-Savart law. Biot-Savart, I think, were two French engineers or physicists or scientists who were the ones to cough this up. It basically says, here's what's happening when we observe what's going on with a wire carrying current. It produces a magnetic field. And really, to me, I mean, it's funny how when you step back and look at nature, apparently nature is adhering to some kind of cross-product relationship. And it turns out that nature actually uses cross-product in many applications. So there are a lot of cross-product relationships in nature. And you've encountered some of them already. You've encountered them with torque analysis and angular momentum analysis. We're encountering them now with magnetic fields, and the list goes on and on. So it's interesting how nature itself seems to have a dot product personality at times, a cross product personality at times, a tensor product. So think of tensors as cross products, or think of tensors as vectors on steroids. So it's funny how, and that's reflected in the math. So here's the bottom line. We're going to apply the Biot-Savart law to figure out what the net magnetic field is at point P. So I'm going to break things up into chunks, into segments. And I'm going to erase my little right-hand rule, PopCan right-hand rule. I think I'm going to redraw those later. But let's do this. Let's do the engineering things and take complex problems and break them up into smaller, bite-sized chunks. So I'm going to call this straight wire segment A, this curved wire segment B, this straight wire segment C, and this curved wire segment D. So let's just jump into it. So we're thinking, well, before we jump into it, let's do the calculus thing. Let's identify a differential element here within this wire. I'm going to move this away. So this should really start to sound familiar to you. Maybe this approach was already familiar to you, but if it wasn't before this class, hopefully it is now. I'm going to break up this macroscopic wire into a microscopic element or differential element. And that's what I'm doing right now. This is a teeny tiny little bite-sized chunk of that straight wire. And as usual, we have to name it. Well, a good name might be, well, I'll start with size. Let's give it let me kind of go in order. We have to give it a size. So the size here would be ds. That's the size. ds. ds is the size. What's the magnitude? The magnitude would be differential I. It's carrying some. Actually, we could just call it I. So what is the current going through this green differential element? It's I. What is the size of this green differential element? It's ds. What is the location of this differential element with respect to Probert? That's given by a position vector right here. This purple vector, let me make that thicker. This purple vector is just a position vector that we look at and say, okay, there is the location of this differential element with respect to Probert. And then there's another thing we'll use, this unit vector. So I'll call this vector R, position vector. And then we're going to use a unit vector, which is the same thing, only unitized. So this is what the unit vector looks like. I guess right here. All right, ready, set, go. Okay, and I'm going to label that orange vector R hat. So what is R hat? R hat is a unit vector that points from the differential element that we're biting off to Probert. What's the relationship between R hat and R? It's the same direction. R hat is just a unit vector. So for example, if the magnitude of vector R was 3.5 meters, the magnitude of R hat would be 1 meter. So because we unitize it, and it's basically just a pointer. It's a indicator. It's like a directional arrow that says, hey, you are here, green differential element. You are right here. And this R hat vector, once again, is just pointing the direction toward Probert. Okay, so that's setting up. That's sort of the standard differential calculus, in this case, integral calculus approach, differential and integral approach to making complicated systems simple, because that's just a little teeny tiny point. So number one, okay, I'll start. The magnetic field at point P is equal to mu naught, the permeability of free space, times the current going through this wire element over 4 pi integral of this. So instead of just, now here's where I'm going to go to magnitude angle format. So I'm going to switch from cross product representation to magnitude angle representation. So what is the magnitude of ds times what is the magnitude of R hat times what is the angle between those two, all over R squared. And remember, when I switch to this magnitude angle representation. Theta is the angle between the two neighbors. Okay, so from here, what is the angle between ds vector and r hat vector? They're right here. Oh, you know what I don't have? I don't have my ds vector. So I'm going to do that right now. Here's my ds vector. It looks like this. This is my ds vector. All right, so a little note. Number 2. So the magnitude of the ds vector corresponds to the length of current element. Super small when we talk about calculus. The direction of ds is same as I. So this is a convention. This is a convention. So how did I know to draw my ds vector in the direction that I drew it in? And that's because it aligns with the current direction. So that's why I drew this green vector the way I did. So if you now look at my green ds vector and my orange r hat vector, what is the angle between them? 180. What does the sine of 180 equal? It equals 0. So at this point, I guess I can say number 3, sine of theta equals sine of 180. So therefore, B, the magnetic field contribution at point P due to segment A is equal to 0. And you know what? We'd have the exact same conversation for segment C, B subscript C equals 0. Same exact conversation with one little nuance here that I'll throw in just because this is the real story. Here's my circuit element. What's the size of that circuit element? ds. What is its location? It's r away. And anyway, and everything's identical. Everything is identical for segment C as for segment A, except one thing. This is my ds vector. In this case, my ds vector is pointing in the same direction as current, and this is still my r hat vector. My r hat vector, the job of r hat is to point from the element, the current element, to probert. So you can see orange and green, that's theta equal 0. So that's the only little nuance that is worth mentioning. Theta equals 0 for here, and theta equals 180 for here. So maybe I'll just get rid of this. So that's a lot of talk to basically realize that there's no contribution between segment A and segment C. They don't make any, they carry a current, but they don't produce any magnetic field. Well, actually, you know what? That's worth mentioning. Segment A, so I guess what's a good way? A and B, A and C, I should say. A and C, they both carry current. So that's good to know. I mean, that's worth mentioning. Obviously, they carry a current. They produce a magnetic field. So if anything, if there's current flowing, you will have a magnetic field that gets created. So yes, it carries current. It produces a magnetic field. But at point P, B equals 0. Just because of the orientation between the circuit element and the point P. Okay, so that's, I think, worth mentioning. Now let's talk about segment B. So number 4. Segment number 4. Let's look at segment B. So I'll say this. The magnetic field produced by segment B, I guess I'll subscript it like this. That's a good idea. Maybe I could have said subscript A. The magnetic field produced at point P due to the current flowing through segment B is equal to, once again, BO sub R, mu naught times I. And I is the same everywhere, all over 4 pi. And then I'm going to do the same thing just for reinforcement. I'm going to, magnitude angle is the magnitude of ds, the magnitude of R, and sine of the angle between them, all over R squared. And different, though, this is going to be different, although I will once again just state the obvious. What is theta is referring to the angle between R hat and ds, which means I have to draw all this stuff. So here's my ds element. I mean, let me just make it like just some weird, oops, I erased something. Okay. Fight the good fight, go through, don't leave anything to the, I was paging through some exam submissions, lots of good scores. I mean, it's too early to tell, but the average from yesterday might be the highest one yet, although that could change. But just I grabbed a stack, and there were a couple exams I think they had all right answers, but like very brief, like too brief on the explanation. So let me maybe remind everyone that you have to do more than get the right answer. You kind of have to explain what you're doing. Because at this point, at this stage of your development, you kind of have to realize the importance of that. So anyway, I'm just buying time as I draw my differential element. So there's my differential element. Here's my position vector. What's the location of that differential element? And we'll need this position vector. This position vector, well, right here. It's located that far away. What's the unit vector look like? The unit vector is the same as the position vector, just unitized. So that's my position vector, R hat. This is my position vector, R vector. What's your vector, Victor? This is R vector. What else do I need? I need the size. The size of this differential element is still teeny tiny ds. That's the size. I need to worry about a ds vector. My ds vector is different. It's tangent. It's tangent to that arc right there. So this is vector ds. Okay. How did I know to draw that in the direction that I drew it? Because it follows the direction of the current. And if you notice, I mean, if my current's flowing this way in segment A and segment C, it's flowing this way in segment B, and it's flowing this way in segment D. So that's how I'm getting that ds vector. Okay, so now let's go back to BO sub R. Number 5 says the magnetic field created at point P, the magnetic field created at point P due to segment B equals mu naught I all over 4 pi integral of ds. What's the magnitude of ds? Here's the magnitude of ds, just ds. What's the magnitude of R hat? The magnitude of R hat is 1. What's theta? So, this is a lot of stuff I'm just blurting out. The magnitude, the magnitude of any unit vector is unity, 1. So the magnitude of R hat is just 1. And in this case, theta does not equal 0. Theta equals 90 degrees because you're looking at the angle between the ds vector and the R hat vector. In other words, you're looking at this angle right here. What is the angle between green and orange? And that answer is 90 degrees. So sine of 90 degrees equals 1. Pretty good. All right, all over R squared. Okay, and then I think I'm going to do another common substitution. Just again, remember what the whole big picture is here. You're going to capture an integral in terms of material and geometric properties. Capture the material properties, capture the geometric properties, and put them into a coherent integral that's integratable. And it's useful saying those two things, because right now, well, actually, you know what? We're kind of done here. We're actually kind of done here, but I'm going to do this anyway. I don't think I need to do this. Maybe I could just integrate ds. The integral of ds is s, and s is that arc length, so it'd be 2 pi over whatever that. Anyway, let me not do that. So forget what I was just ranting about, and let's just say, okay, the magnetic field at point B due to segment, the magnetic field at point P due to arc B, I'll say it like that, equals mu naught. We know what that is. I, that's a given. 4 pi. And then you know what? I'm going to pull out the r, 4 pi r squared, because r is a constant. R is a constant. It is not a variable. It's a constant. And for arc B, that's given. For me, arc B is given as having a radius of 0.138 meters. So R is a constant that can come out of the integrand. And then I'm going to do birth of a radian. All sorts of good sidebar stuff. If the definition of theta is S over R, that means arc length S equals R theta. And if I just differentialize, ds equals R d theta. And again, this is what I refer to as birth of a radian. And I'm just going to substitute R d theta. Okay. And I think we're done, because I know my limits of integration. I'm going, do I know that? Yeah, theta is 74 degrees. Theta is 74 degrees. And then here's a question. Well, before I do that, let me just do some more operational steps. The magnetic field at point P due to arc B is equal to mu naught I all over 4 pi r. The integral of d theta is theta. And what are my boundary conditions? From 0 radians, why do I have to use radians? Why do I have to use radians and not degrees? Would it be a mistake to use degrees? And the answer is yes, it would, because as soon as I made this substitution, I'm relegating myself to radian measure. So that's what I'm saying, from 0 degrees. So maybe I'll call this this boundary over here. This is 0 degrees. So I'm going from 0 degrees to, in my case, 74 degrees. So then I'm just going to convert from degrees to radians, which I'll just do 74 degrees times pi over 180 radians. And I think that's good. So what we have to do now is, you need to let me know if I've made any mistakes. And if I haven't made any mistakes, let's get a number. We're not done. We have one more segment to go. But actually, let's get a number on this right now, even though we could hold off. But let's get a number on your calculator. Let me write down mu naught. Mu naught is the permeability of free space. So mu naught, it's a friendliness factor, equals 4 pi times 10 to the minus 7th. And I think it's Tesla meters per ampere. Okay. And then use your own numbers. And then we'll do the last chunk of this.
So in this case, would R be RA value?
R is talking about the position from this element right here to where probert is. So this distance from that element to point P is R subscript A. So I get a number. We actually have to worry about direction as well. So you need to get a number, and we need to get a direction. So there's actually a lot of conversation that has to happen about direction. So the magnitude is something, 3.94 E minus 7 Tesla. What's the direction? So this is the magnitude of the magnetic field. Write it like that. The direction is, and you could do this a bunch of different ways. I'm going to do the cross product method. So to find it, and we do have to worry about the direction because I have a top wire and a bottom wire. What if they destructively interfere? What if they constructively interfere? So direction matters. So you know what? I'm going to do this. I'm going to curl. That's the expression. Curl ds, my vector ds, into my r hat unit vector. Okay. So in other words, I am going to curl. I'm going to assume the right hand position, the pop can right hand position is frozen in place, and with my hand frozen in place, as if I dipped it into liquid helium. It's just frozen. If I curl this vector ds, if I curl vector ds into vector r hat, it means I'm going to swing my fingers. I'm going to curl it by basically sweeping it in that direction. And if I do that, if I'm sweeping ds into r, and I do have to sweep ds into r, I'm not sweeping r hat into ds because the cross product is set up as ds then r hat. If I'm swinging ds into r hat, and I'm keeping true to my right hand rule pop can position, that's negative k. So the direction, it's into the screen, it's into the page, it's into the screen. The direction is there for negative k hat. So that's fine. Negative k hat. And again, I have to worry about magnitude and I have to worry about direction. And then the last thing we do here is step number 8, switching to green. What is the magnetic field at point P due to segment D? So I can kind of fast track this, but I do want to take the opportunity to reinforce. So I'm going to get rid of all of that stuff because now we're looking at segment D. This was segment D, this bottom segment. This is D right here. I'm going to, once again, indicate my fundamental setup. There's my little element. And this is important because things are a little bit different. It's still called DS. It still has a unit vector pointing toward the point that we're interested in. There's my unit vector. Here's my DS vector, and this is different. DS vector is in the direction of the current, and it's tangent. There it is. All right, like that. So this is vector DS. Okay, and this is vector r hat. So you can see the angle between them is once again 90, but you can also see the cross product is positive k. This is r hat. So anyway, this is why it's going to go faster because you're hopefully seeing those right away, although I won't gloss over it too much. All right, so we have Biosvar says mu naught I hat all over 4 pi integral. What's the magnitude of vector ds? The magnitude of vector ds is just ds. What's the magnitude of r hat? It's 1. What's the sign of the angle, or what's the angle between green vector ds and orange vector r hat? It's 90 degrees. So there you go, all over r squared. And that's how we are very quickly getting to the magnitude of the magnetic field at D is equal to mu naught I hat all over, and I forgot R. Yeah, well, let me not do, all right. Integral, birth of a radian says ds ds, I'm just going to substitute r d theta. So it's identical, which is why all you have to do is take mu naught times I all over 4 pi. And then this is what's different. I'm going to call this R. And for me, I guess this is R sub, well, for you too, this is R subscript B, just like this was R subscript A over here. So that's a good thing to add. Times the integral of d theta is theta. And I'm going to go from 0 once again to 74 degrees, converting to radians. Okay. And then you're going to get an answer. You're going to get BD equals some answer. And you're going to do right-hand rule. And you should satisfy yourself that the direction you get when you curl ds into r hat, that's positive k. So that's not negative k, it's positive k. So let's finish up this problem. Oh, so the magnetic field at point P, the net, is just going to be whatever you get from whatever contribution you get from arc B plus whatever contribution you get from arc D. And we have to be aware of plus K and minus K. So for my segment B, for arc B in my case, I would actually have to say that that's a negative 3.94, and I have it stored in memory. So that's a negative value because it's going into the page. So we're looking for the difference. Tesla plus BD, and in my case, BD is coming out of the page. So that gets a plus 4.854 E minus 7 Tesla. And the answer is negative. I get a negative 9.1467 E minus 8 Tesla. And it's into the page, or negative, that's fine, direction. My result is, I mistakenly wrote down this as negative. My result is a positive value. So that's why I agree that it's out of the page, out of page, or plus K hat direction. All right, so let me see how things are going. Well, everyone's done. Most people are done. So, so there's a lot. Right-hand rules, Biot-Savart, the whole calculus approach. What's not to like? Let me go ahead and open up the next quiz so you can do your read through. Chapter 29, quiz 8. This is another Biot-Savart problem. So again, this is the fundamental. This is solving problems the hardest way possible. We're gonna learn a shortcut, but this is the hardest way, and you always have to learn the hardest way possible. I think that's a John F. Kennedy quote. Why do we go to the moon? We choose to go to the moon not because it's easy, but because it's hard. So I knew that sounded familiar. But anyway, it's 142. Okay, so now you should be able to go look at chapter 29, quiz 8. Okay, so your first thought is probably this looks a lot like the problem we just did. And the answer is it is a lot like the problem we just did. But there's a few differences here, and it's those differences that make this worth doing. Plus, it's a Biot-Savart problem. So on exam 4, if I give you this problem and if I basically say, hey, solve this however you want, because there are different ways of solving this, you can solve it any way you want. If on the other hand, if I say solve this problem using Biot-Savart for each of these 6 segments, A, B, C, D, E, F, then you kind of have to do the strict Biot-Savart approach. And I mentioned that because we're going to learn something. Well, you've already learned Ampere's law. There are shortcuts to doing this, but what if you are precluded from using a shortcut? So I'm going to start here. Because this looks so familiar, I'm going to throw it in well, I don't have to do this. I'm going to say The magnetic field, so once again, you hire Probert. Probert's standing here at point P, and Probert needs to tell us what the magnetic field is. Kevin, I guess I would just say, again, refresh your screen, log out, log in, and if this quiz just disappears, just let me know after class, and we'll make things right. So hopefully, just refreshing or relogging in helps.
Yeah, I've tried all that. It's not working, so I'll just follow along. And
okay, and let me know.
Yep.
You're good for it. Your credit is A-okay. All right, so I can say this. Well, what is the magnetic field at point P where all of those, where Probert is standing due to all of those wire segments? And I'm going to say the magnetic field contribution from A is the same as from C is the same as from D. It's the same as from F. All right. And they all equal 0. Because you can't just say that, and you can't really just talk your way through it. At the very least, you basically have to say, well, okay, for each case, for A, C, B, F, for each of these segments, for each of these current carrying segments, there's a segment for D. Here's the little element for A, for F, for C. In every case, well, I'll do a quick, here's the R hat vector for each of them. Let's just do that quickly. Here's R hat for A. There's R hat for D. There's R hat for F. There's R hat for C. Okay, let's do DS. Here's DS. Here's DS at A. Let's see this. There's DS. Here's DS at D. Here's DS for F. That's kind of different. And here's DS for C. So let me just label those. Green is the DS vector, their vector, DS vector, DS vector, DS vector. And again, the orange are the R hat vectors. So now you can just basically, as shown, you can say theta for A equals theta for D equal 0 degrees. And you can say theta for C is the same as theta for F equals 180 degrees. So sine equals 0 in all cases. So we quickly toss out segments ADFC, and we're just going to focus on these two segments. And you're thinking, well, even that's easy because this is a lot like the problem we just did. And it is a lot like the problem we just did, B and E. So let's make quick work of this then without losing points due to lack of explanatory comments. Number 3. Okay, so let's talk about the magnetic field at point P due to the current in arc B. It's mu naught, Biot-Savart says mu naught I hat over 4 pi integral. The magnitude of ds is ds. The magnitude of r hat is 1. And then we have to worry about, I guess, the angle, theta b all over rb squared. So these, and I'm doing a better job subscripting here. So let's draw the representative element for segment B. I'll just choose this one. Here's a little teeny tiny element. The size is ds, differentially small, infinitesimally small. The ds vector is in this direction, tangent. So that's ds vector. My r hat vector is pointing towards the center of the circle. And you can see that's 90 degrees. R hat. Okay. So number 4 then becomes this contribution equals mu naught I. Oh, and we have 2 different currents. So it's going to be mu naught times I1. I1 is what's flowing through segment B. Mu naught times I1 all over 4 pi. The integral, so in my integrand, if I look at the integrand, my numerator becomes this, ds. My denominator is r subscript b squared. And then I think at this point, you can kind of go off and running. I'll do this. I'll throw this out. My limits of integration I'm looking at the bottom. I'm looking at segment B. So it's 0 radians. And in my case, this upper limit would be 180 degrees, also known as pi radians. So, and then you're going to do your substitution. You know how to substitute ds, birth of a radian. ds is going to become, and let's use subscripts, it's r of that bottom arc b times d theta. So it's business as usual. So and before because I'm kind of wrapping up, I'm just going to throw it over to you. What's the angle? So once again, I'm going to use my sanctioned right-hand rule. I'm going to cross ds into r. Ready? Here goes. There's d, and no matter where I do that, no matter what point I select on the bottom arc B, I'm always going to get the same direction. It's always going to be plus k. So you're going to come up with a number, and you're going to come up with a direction. And so this equals some number, and it's in the plus k hat direction. And then you can just rinse and repeat for segment E. Repeat for segment E. And then the direction is, I'm going to do that whole right-hand rule game again. So here's my sample segment. Here's my r hat vector. So kind of fast tracking this because I think I can. There's my r hat vector. Okay. Here's my ds vector. I have to worry about direction. So my ds vector is in this direction. So once again, theta is 90 degrees. Theta is the angle between ds and r hat. That's 90 degrees. And if I do my right-hand rule, I'm swinging ds vector into r hat unit vector like that. And that means a minus k. So repeat for E and make sure you agree that the direction you're going to get a numerical result. So cough up your numerical result. And then I'm getting minus K, and I think probably we all are, but you should question that. Look at everything I write down skeptically. And then that's it. You're going to get the right answer for part A and B. And then you're going to do the whole thing over again, except there's one little change for C and D. What if I1 is reversed? So you can go ahead and finish this. I'll put myself into a timeout. But part C and D it's going to be the identical approach. You're just going to flip the direction of I1. And if I flip the direction of I1, that means that's going to be a negative K direction or into the page. Okay, so finish this problem. Not again, I'll just bide my time in my cone of silence unless I'm needed for something.
Professor,
Yep.
so we would get an answer in Tesla, right? And then we have to convert.
Yeah, right. Right. So 1 Tesla equals 1e6 microtesla. Solenoids are one of these things. They appear in very practical applications and very exotic applications. You're looking at this on my screen right now. You're looking at a solenoid that was part of the Large Hadron Collider, which was this gigantic physics experiment in Switzerland that was aimed at finding like the fundamental particle in nature. And you can see, I mean, look at the workers down here. I mean, there's a whole bunch of people working down here, and look at the size of this solenoid. So you have like these incredibly large solenoids for, you know, audaciously large physics experiments. And then you have automotive starter solenoid. So on literally the extreme other end of the spectrum, in your car, we all have these little solenoids that basically start up your engine. Here's a picture right now. Let me just get a picture of this. This is a good picture. So this little gizmo is, again, in our cars. And when you turn the key or press the button, you send some electricity through these wires, and you get a magnetic force that turns this gizmo and starts your engine. So again, spanning automotive chargers all the way to the Large Hadron Collider. So just wanted to, once again, talk about how solenoids are pretty pervasive. So now you have a solenoid, and that's what I drew here on the screen. It looks like a slinky or a spring. Basically, I mean, if we went through the progression, what are we talking about here? We talked about a differential element, a super teeny tiny differential element, so just DI, some differential element. And then we talked about what happens with the magnetic field surrounding a straight wire or a straight line. So we graduated from a point element to a straight line, and then we graduated from a straight line to a loop. And then we're going to graduate from a loop wire in a loop. And then we're going to graduate from wires in a loop to a stack of wire loops. Stack of wire loops is called a solenoid. So this is what a solenoid is. It's a stack of wire loops, looks like a slinky. And then the final destination would be a twisted solenoid. A twisted solenoid, and you find these everywhere too. A twisted solenoid is called a toroid, as in Taurus. All right, so you have this solenoid, and from last time in the lecture video, we like solenoids because they create a very uniform magnetic field. And a magnetic field is, we like magnetic fields because they store energy. So if you just look at this from an energy point of view, everywhere inside the solenoid, I have uniformly spaced magnetic field lines. So there's one, and then here's another one. And then again, just everywhere and anywhere inside of the solenoid, I've got a bunch of these magnetic field lines. One second. Tech issue. All right, so I'm trying to draw a whole bunch of uniformly spaced magnetic field lines. So maybe this is sufficient. And again, this is why we like solenoids. They're the magnetic equivalent to a capacitor. Capacitor stores a whole bunch of electric field lines, electric potential energy. So that's good. So rather than keep drawing these magnetic field lines, I'm just going to draw the resulting magnetic field vector. So I'm just going to get rid of these and aggregate them or represent them with a representative magnetic field line that looks like this. So all of those magnetic field lines produce this magnetic field vector like this. Okay. This is magnetic field vector B. B for magnetic field vector going along everywhere inside of that coil. Then we have an electron that's spinning around and around in a circle according to the problem. The problem is saying you have an electron and this electron is just doing a whole bunch of orbits in a circle over and over again inside of this solenoid. So something like that. And maybe if we wanted to give it a direction, maybe we're saying it's going this way. Whatever the direction is, it's going in a circle. An electron moves within the solenoid in a circle with a known radius perpendicular to the solenoid axis. So here's the plane of my circle right here. And the plane of the circle is perpendicular to my solenoid axis. So that looks good. We know the speed of the electron, find the current in the solenoid. So that's what we're after here. So this is a centripetal motion problem. So number one, well, if the electron travels in a circle, if the electron travels in a circle, you know one thing. You know that there's a centripetal force. You know there's a centripetal force acting on it, and you know centripetal force is mv squared over r. So electron must be subjected to this centripetal force. So generically speaking, that's true. Centripetal. Centripetal means center seeking. Centripetal force. So that should be very apparent. Anything moves in a circle, it's moving in a circle because there's a centripetal force acting on it. Generically, that's true. Now, here's the question. What is the agent of the centripetal force? Is it a string, or is it a spring, or is it gravity, or is it the normal force? Like, for example, gravity is the force that makes the moon move in a circle around the earth. Whereas when you exit I-275, and if you exit onto a ramp, if you've ever exited onto an exit ramp that's like banked, it's the normal force that's providing the centripetal force. In this case, though, F sub C, the generic centripetal force, is brought to you by the magnetic force. The magnetic force is the agent. So the F sub B makes the electron move in a circle. Okay. And that's useful because that's useful at least for the next step. So we can say, okay, well, here's centripetal force, mv squared over r. Here's the magnetic force, qv cross b. All right, so that's my next just knee-jerk reaction. That this is the centripetal force, and it is instantiated by this magnetic force. So we need to find out the current in the solenoid, and right now I'm not seeing it. So where's I subscript S, solenoid current? That's our $sign. So I'm not seeing the $sign directly. It's probably buried here somewhere. But right now I'm not seeing it. But that is what we're after. So I'm just going to keep developing. I'm just going to keep hammering on number 6. So let's see. Well, with subscripts here, we're talking about the mass of an electron. We know what that is. V. Do they give us the velocity? No. Well, yes, they do. The speed of the electron is 0.036 times the speed of light. All right, so they do give us that. So I'm just going to leave that. So that's mv squared over r, and they do give us r. So that left side is looking ready to go. mv squared over r. That's the good news. The bad news is I'm still not seeing the $sign. So for the right side, I'm going to go to magnitude angle format yet again, QB sine theta. And then you have to ask yourself, what is the angle between that B vector and this V vector here. Well, I'll draw a sample V vector for the electron. So for the electron that's, again, spinning around in this circle, I'll just draw some arbitrary vector tangent at that point. Again, just arbitrarily selecting it. This is the velocity of the electron. It's just some arbitrary point, whatever, along that red path. Okay, so everywhere V and B are perpendicular. So I'll just do that. V and B are perpendicular everywhere because of my very insightful diagram. So what if I just wanted to draw a velocity tangent, a tangent vector, like right here, for example, tangent. So this would be V at that point, and convince yourself. So convince yourself that every purple vector is perpendicular to that green vector. So sine of theta equals 1. So still not seeing the dollar sign, but keep fighting the good fight. Hope springs eternal. I have m of the mass of the electron. The v's cancel. So I have mv over r. Feeling good about that. Equals qb. Number 9. Well, I know this from kinematics. I know velocity is distance over time in the crudest way possible. Velocity is distance over time. We could like take a very formalized kinematic approach to say the same thing, but we all know velocity is distance divided by time. For one circle, then we have velocity equals distance. Here's the distance of a circle. It's the circumference, 2 pi r over time. How long does it take an electron to complete one cycle? Capital letter T. Okay. All right, so I'm going to make that substitution. Number 10, mass of the electron times 2 pi r all over T. Oh, wait a minute. I didn't need to make that substitution. I kept thinking, I keep forgetting that they gave us the velocity, so I'm going to go ahead. Everything I said is true. It might be useful in the future. I don't think it's going to help now. So anyway, number 11, I guess because we're still trying to peel things apart. Mass of the electron times V over R. So back to number 8, chalking up steps 9 to good, clean fun. MV over R equals Q. And now here's another idea. Here's another layer I can peel. Mu naught N I of solenoid. And there's the dollar sign, because this was derived using Ampere's law, and you should hopefully have a very good appreciation for that. Right here. This is from Ampere's law. Ampere's law was used to say the magnetic field going through the interior portion of a solenoid is mu naught, the permeability of free space, the turn density times the current going through the solenoid's wires. So this is the dollar sign. So I think then that's the dollar sign. Let's see, do we know everything here? Let's just go through a checklist. The mass of an electron. Mass of an electron is 9.11 times 10 to the minus 31st kg. Do we know the radius, the turn radius? Yes, that's given. Do you know Q? Yes. The charge of an electron equals 1.6 E minus 19 coulombs. Do you know little n? Yes, you do. Remember, little n stands for turn density, the number of turns per length. And that's actually given to us as 130, for my number, 130 turns. Turns is not turns is not a unit, so I just won't even write it down. So 130 turns per centimeter, or 130 turns per 0.01 meter. So that's little m. So you have everything now. You should do the dimensional analysis and solve for I subscript S. Velocity, they told you the velocity. The velocity with my numbers is 0.036 times the speed of light, and this is the speed of light, 2.998 e to the 8th meters per second. Okay, you guys, and that's it. That's it. So take your time. I will go into timeout for a minute. For those of you who are done, go ahead and access our last quiz. I think we might do something after the quiz, but for now, the quiz portion will conclude with Chapter 29, Quiz 10. Still quite a few people working, so I'll stand by for a bit. All right, well, last quiz then. As soon as I said that, then I just checked in, like almost everyone's done. So, and if you're not done, no need to worry. The extensions are available for a nominal fee of $1.38. But for now, let's go ahead and do the last quiz for today. Do the read through. It's going to be, this is similar in some ways. It's a solenoid with an electron flying through it, but some pretty profound differences. So this is a solenoid. And by this point, hopefully, due to my repetitive descriptions, this is the magnetic field vector for the solenoid. So this is B vector. That is the magnetic field. That is the solenoid's magnetic field vector. Again, it's chock full of magnetic field lines all over, occupying every point in space inside of that solenoid. Yes, you do have edge effects, but we're ignoring those edge effects. All right, so now you shoot an electron. So here's an electron right here. This is an electron. And you fire this electron at an angle of 31 degrees with respect to the longitudinal axis. So there. Like I'll draw it even like this. All right, so this is the electrons. You shoot an electron with that angle into the solenoid. So this is E minus, which is the symbol for electron. Okay. And then the question is, it's going to start spinning around in a circle. The electron itself will start corkscrewing. We'll talk about it. But the electron itself, when it enters that magnetic field, it's going to start corkscrewing like this. The electron itself will be tracing out a helical path. Helical as in helix, as in slinky, as in spring. So once the electron enters that magnetic field of the solenoid, it's going to be doing this helix thing from the very beginning of the solenoid to the very end of the solenoid. And the question is, how many revolutions does this electron make by the time it gets to the end of the solenoid? So maybe I'll try to, well, I don't want to clutter things up too much, but once again, let me just repeat this. We're going to find, we're not going to just like gloss over it, we're going to actually talk about how the electron will, when it encounters the solenoid's magnetic field, start to corkscrew and be trapped inside of the solenoid. In fact, you see this in nature. The northern lights are an example of this. Nuclear fusion is an example of this. There are many instances where charged particles are trapped by a magnetic field and they just corkscrew. So again, theoretical or exotic examples and everyday examples. Well, anyway, lots of examples. So here's what one revolution looks like. We're just going to say, hey, how long does it take for this one, for or how many of these revolutions, I should say. So maybe I'll just try to say, here's a revolution. So I'm just drawing this black line here to represent this. This is a revolution. This represents one revolution. So you can see I have some number. The electron is going to enter, and when it enters, it's going to start corkscrewing. Maybe I'll draw it over here too. It will look well. Actually, I think let me adjust this because I think the electron enters at the beginning of the solenoid. So let me just do a little bit of housekeeping here. The electron, because I'm reading the question. The electron enters the solenoid. So the electron is entering the solenoid. This is probably a better way to draw that. So the electron is literally traveling along the entire length of the solenoid. Like that. Okay. So the question is, how many of those revolutions happen from the very beginning to the very end? And then again, the electron is going to enter and then start corkscrewing. Good enough. One more time. Okay. All right, so here we go. How many of those revolutions are completed from the very beginning of the solenoid to the very end of the solenoid? And once again, uniform circular motion. I'm going to do this. I'm going to break my velocity component. I'm going to break my velocity into two components. This is the y component. Let me use blue. And I'll do it over here. This is the x component. And this is the y component. And let's label this. So this is the electron's x component of velocity. This is the electron's y component of velocity. Let me just clean this up for a bit. And this is the given velocity. So I'm going to call this is v. All right, so that looks better, I think. Okay, so now let's talk about, oh, I got to move my electron. Let's talk about Vx and Vy. And here's my electron. My electron is right there. All right, so that's better. And the angle, it says my entry, it makes an angle of 31 degrees with respect to the longitudinal axis. So that looks like this. This is the longitudinal axis. So this is my 31-degree angle. This is theta, my angle of incidence. And if that's theta there, that's theta right here. So I'm learning a lot. Well, I'm breaking things. I'm intentionally looking at the x velocity and the y velocity because it's this y velocity. This y velocity results in some F sub b acting on electron. This results in no magnetic field, no magnetic force, no F sub b acting on electron. And I'm going all the way back to chapter 28, the start of chapter 28. If charges move parallel or anti-parallel, they don't feel any magnetic force. So V sub X is parallel with B. I better write that down. V sub X is parallel with B. Therefore, no magnetic force. And then I could say here, Vy, check this out. Vy is perpendicular to B. So Vy is perpendicular to B. There's definitely going to be, therefore, there's going to be F sub B does not equal 0. All right, so let's go ahead and once again, start with centripetal force considerations. Let me get rid of this and see. we got to find the dollar sign somewhere. The dollar sign is number of turns, however you want to call that, number of revolutions. And you know what? I guess we can start strategizing like this. So in terms of thought development, in terms of blue skying some stuff, total number of turns. Let's just talk about that. Total number of turns. And I think I can see my way to at least writing this right now. And this might be a good path. Total number of turns is the amount of time it takes to go through the solenoid divided by the amount of time it takes to complete one cycle. So let me just write this down here. Let's just say this is x equals 0, and this is x equal, I'll call it L, I guess, the length of the solenoid. So however long it takes, the amount of time it takes to go from the beginning of the solenoid to the end of the solenoid, in that amount of time, I'm going to complete some number of revolutions. So for example, just for this, in the name of an example, let's say it took 10 seconds. It takes the electron 10 seconds to go from x equal to 0 to x equal L. Let's also say, just for the sake of a fictitious example, it takes 2 seconds to complete one of these orbits like that. It takes 2 seconds for one orbit to complete. That basically means I have five revolutions. Again, using really simple examples, but that's what I do in my head to, I guess, make sure that I'm okay with the total number of turns is going to be the total time spent in the solenoid divided by the amount of time needed for one cycle. So that's my way of thinking through step number 1. All right, so now let's figure all this out. What's little t? Let's do this. Little t equals time required for electron to travel from 0 to L. And we can get that. Ready? It's this. Again, very simple kinematics. If velocity is distance divided by time, then you can say time equals distance over velocity. So in our case here, little t equals distance, which is L, all over velocity, which is Vx, or V cosine theta. Vx here equals V cosine theta. So we're done with little t. We're done with little t. Do I know L? No. So this is an uh-oh moment. Like, so we can say, I know everything there except for L. So I'm just going to say, uh-oh. What's L? Okay. So right now, I'm just going to keep this on ice. I'm just going to keep this in its own little safe corner and say, I'll come back to you later, because I don't know enough to solve at this point. I don't even know enough to find little t. So I'm going to go after big T somehow, I guess, and see where the chips fall. All right. So let's talk about big T. And I'll start with the same old centripetal motion, uniform circular motion. Because this electron, since Vy is perpendicular to B, electron experiences a centripetal force. So that is a very good part of this problem. Since this y velocity is going to be perpendicular to the magnetic field, it experiences a centripetal force brought to you by the magnetic force. How do I know it's centripetal? Right-hand rule. Centripetal force. So I can say that centripetal force is going to be that magnetic force. So just do that right-hand rule thing again. Maybe I'll just say, okay, if I'll make a copy of this. Here's V sub y. So I'm just going to do this just as a sample, just because I want to convince myself that, all right, well, if this is V sub y, if my electron is somewhere right here. Let's just say my electron is sitting right here at this particular point. V sub y is in that direction. So my fingers go into my finger, and I'm going to use my left hand because it's an electron, but my fingers go in the direction of the magnetic field. My thumb points in the direction of the velocity. So everywhere I play this right-hand rule game, this flat hand right-hand rule game, everywhere I play this game, there's going to be a magnetic force pointing towards the center, the same center point. So that's how I'm convincing myself and convincing the person grading this exam that, yes, this is a centripetal force. Okay, so number 4, the centripetal force is mv squared over r. So once again, yeah, that's centripetal force. Here's my magnetic force, because the centripetal force is the magnetic force, QVB sine theta. I'll just go to magnitude angle. But now I have to be careful. Wait, I got to use subscripts. Wait. So that's generically true. Generically, yes. This is my centripetal force, and my centripetal force is the instantiation of the magnetic force, and the magnetic force is always pointing to that center point. So just constantly repeating things. Okay, number 5 then. But wait, I'm saying what? Because I need to worry about subscripts. This is the mass of an electron. And that's not just any old V. That's V subscript Y squared. So this is why, again, subscripts are critically important. MV squared over R, that's my left side. What do I have to worry? Well, Q is, I'm just going to leave that. Q is the charge of an electron. I know that, 1.6 E minus 19. V, so nothing to do. Nothing to do. Oh, yeah. Here's the question. Should this just be V, or should it be Vx, or should it be Vy? And then actually it should just be V. MV QVB sine theta. So let me just dwell on that. This is just regular old V. This V here is the electron's entry velocity. And I'm not doing V subscript X or V subscript Y, because that's what sine theta. Sine theta is going to basically figure out the degree of perpendicularity between my entrance velocity vector that I'm indicating here and my magnetic field, which is the red vector. All right, so let's run with this. Still not seeing big T, but I think I might know where big T is hiding. I'm just going to do another one, number 6. I think big T is hiding in that velocity term. So let's see, mass of an electron times V sub y, and I'm going to write V sub y is V sine theta because of trig. Vy equals V sine theta, and I'm squaring that all over R equals Q, and I can see that V sine theta, so I'm going to say QB sine theta. And you can see things are starting to get simpler. This B sine theta cancels with one of, I'm sorry, I need backspace, I forgot. This should be QB V sine theta. So let me try that again. This V sine theta here cancels with one of these. So I'm left with something simpler. Number 7 says mass of an electron times V sine theta all over R equals QB. Still not seeing the dollar sign, but things are getting simpler. And I think my dollar sign lives in that velocity term. So I need to be careful here at number 8. I'm going to say V sine theta, which, by the way, again, is just V subscript Y. And V subscript Y in my conversation of centripetal force. So I'll make a note of that. Equals distance over time, 2 pi R. That's distance over time. And there's my dollar sign. So to me, there's a lot. There's a ton of places to make missteps here. So that's what I'm trying to really be fine-grained. V sine theta is Vy. And I want to stress the fact that that V does not equal 2 pi R over T. V does not equal that. This is not the centripetal. This is not the centripetal force velocity. This is not the velocity you see in mv squared over r. So whenever you write down mv squared over r, this velocity is the tangential velocity. This must be v subscript y, or the tangential velocity. The velocity that's tangential to the circle's perimeter. So anyway, maybe beating that a little more than I needed to, but it's the details. So let's update. Here's my new number 7. Mass of the electron times velocity times v sine theta. So again, this is v sub y. I'm going to replace that with 2 pi r all over t. That's my numerator. Here's my denominator, and here's my right side. And you can see that this r cancels with this r. So I'm going to get t. I'm going to get big T all by itself, and then I think I'm almost done. Because I got little t, or I got an expression for little t. Here's big T all by itself. Big T all by itself equals 2 pi mass of an electron over QB. Okay, that's big T all by itself. Do I know the mass of an electron? Yes. Do I know the charge of an electron? Yes, but I'm still writing down I don't know B. So I do know I have a solenoid. I do know that, so I'm going to just rewrite B equals 2 pi mass of an electron over Q. And here, for I think the 3rd or 4th time, and it's the heart of one of the labs you're doing on Tuesday, I'm replacing this B right here with the expression for the magnetic field inside of the solenoid. It is mu naught little n times the current going through the solenoid wire. This was derived using Ampere's law in your green sheets ad nauseum, and that's why I'm making this substitution. So this B right here is substituted with this, the magnetic field inside of a solenoid. So that's the substitution. So let me update. So now am I done? Let's see, with big T. So now I'm going to write down So another What's N? And the answer is little n, sorry. What's little n? The turn density. What's little n? The little n here equals turn density, number of turns per length, and then aha. Now all of a sudden I can start breathing again. There's L. So an aha moment is upon us. All of a sudden L appears, and I'm counting on it canceling out. So I'm writing aha, and I'm feeling like a glass is half full because while I don't know the length of the solenoid, maybe L's cancel. So that's what I'm crossing my fingers for, hoping for. Let's keep going. All right, so big T equals 2 pi mass of the electron all over Q mu naught N, and here's N. N is now number of turns, which is in a unit, per length times the solenoid current. Okay, that's it. Not done, but still feeling good. Number 13. Let's try now. Let's try the little t over big T, because little t over big T is our answer because of this conversation. If it takes 10 seconds to go from 0 to L and it takes 2 seconds for one revolution, that means you've completed 5 revolutions. So here's little t. Little t, I'm just looking here at step 3. Little t is L all over V cosine theta. All of that, that's my numerator. Here's big T, 2 pi mass of an electron all over Q mu naught N times the solenoid current over L. That's the answer. That's our answer. So let's, before we're unleashed, do I know L? No, but I'm hoping, so question, does L, so here's sort of a nightmare situation. Not really, that's overstating it, but question, does L cancel? Does L cancel? Do I end up with L canceling, or do I end up with L squared or L squared? So does L cancel? Anyway, I don't know L. I'm hoping it cancels, but you do the algebra to figure out if it cancels, or maybe if you end up with L squared. And that would be good. If you end up with L squared, you know there's something wrong. You just troubleshoot. Do I know velocity? Yes, my velocity is given. My angle is given. My angle is 31 degrees. The mass of an electron, I'll write that down. The mass of an electron equals 9.11 E minus 31 kg. So I do know the mass of an electron. I do know my angle. I know the charge of an electron. It's 1.6 E minus 19. I know, so I'll just write this stuff down. Mass of an electron, Q is 1.6 E minus 19 coulombs, mu sub naught equals, and you're doing the dimensional analysis, 4 pi E minus 7 Tesla meters per ampere. And you do know I sub S. You do know the current flowing through those wires, those helical wires. So you're done unless there's a mistake. And again, one indication would be you get an L squared. But what if the L's do cancel and you're still not getting coherent dimensional analysis? That's another reason. But you know what? You're on your own. And I'll say this will be it. So you can drop off. You're officially done whenever you want to be, but we're officially done with class material when you finish this quiz. And if you need me to reopen quizzes 7, 8, 9, or 10, or extend those, let me know. Otherwise, that's it for me. We'll see you guys on Monday and talk to you between then and now. I'll hang out online. So just, yep. Questions, anyone? Questions or requests?
Yes. Could you open Monday's quiz quiz 6, last one we did on Monday.
Chapter 29, quiz 6.
Yeah.
Yeah, I'll open that until 4:30.
Thank you.
Okay.
And my solution for doing the quiz is if you open it until 4:30, I can start it at 3:59 because it's still locked until then on my screen.
So which one was that?
Quiz
Kevin?
8.
All right, so I'm opening 6 and 8 until 4:30. All right, will do. I'll do that and see you guys on Monday. Again, let me know any last calls for extensions or anything else. If not, I'll leave my screen up and then open 6 and 8.